Okay, good afternoon. Good afternoon. Can you hear me? Yeah. So today we are going to introduce early effect. And yesterday, uh, before closing the session, we have found that if you have a MOSFET or a BJT with a resistance R here, and you're looking through collector, if you move from collector to emitter, what is the multiplication factor? The multiplication factor is R naught plus some factor K times of R, right? And what is the value K? It is 1 plus GMR naught. It is 1 plus GMR naught into R, but here you have an R pi, so it is going to be R parallel with R pi. So this is something I have derived last class, is it not? But if there is a MOSFET and you're looking through the drain, you have R naught plus 1 plus GMR naught times of R, right? So this is my last rule. And what is my first rule? My first rule is if you see through base terminal, you have R pi. If you see through emitter terminal, you have alpha by GM. If you see through the collector terminal, you have R naught, right? If you see through base terminal, there is R pi, alpha by GM through the emitter and R naught through the collector. And the good thing about BJT is alpha by GM, this is going to be in ohms, right? Or tens of ohms. Suppose this is 10 ohms. Now this is going to be in kilo ohms. And R naught is going to be hundreds of kilo ohms or maybe a mega ohm, hundreds of kilo ohms. So the student should know the exact analysis as well as approximate analysis also. For example, if the in an equation, if you have a factor alpha by GM parallel with R naught in case, then what is the best approximation? A small resistance of 10 ohms parallel with mega ohm. So this is going to be approximated to alpha by GM. Similarly, there is R pi parallel with R naught. R pi is in kilo ohms parallel with mega ohms is kilo ohm, right? Or if alpha by GM plus R naught. Alpha by GM is 10 ohms, R naught is mega ohm. So what is mega ohms plus 10 ohms? It is mega ohm. So these approximations also, because sometimes you don't find the equation that we get in the options, then you have to look for the best approximation. A large resistor in parallel with a small resistance is going to be a small value, right? A large resistance in series with a small resistance is going to be a large value, right? And what is the multiplication factor I mentioned? If you go from base to emitter, then you have to multiply by a factor 1 plus beta, am I right? And if you go from collector to emitter, sorry, emitter to base here, right? Collector to emitter, we have seen 1 plus GM R naught. And emitter to collector, it is alpha by GM plus this resistance R divided by 1 plus beta. So all this we have seen, right? This is a review of yesterday's class. Okay. Now let's include R naught early effect. Yeah, in the coming week, we are going to complete this syllabus, right? He told me Friday, by Thursday or Friday, but we'll see. Maybe one day extra. But next week, we are going to complete the syllabus. But we'll go slowly, right? It's not that just because we want to complete, we should run. No. Even if we want 1 or 2 days, it doesn't matter. So we go slowly. Okay, so this is a review of yesterday's class. Fine or not. Consider early effect. That means your VA is not equal to infinite, right? So your R naught is finite. Consider R naught. This is the common emitter amplifier. Okay, so let's get started. So here we have R naught, and there is no connection between collector and base. So what is R naught? Not equal to R naught parallel with RC. So mega ohm parallel with kilo ohm. That is why this is approximately RC, right? If the examiner includes early effect also, then it is R naught parallel with RC. Now what about this? Let us find the resistance here Rx, if this is R naught. So if you know Rx parallel with RC. So what is Rx? It is R naught plus 1 plus GMR naught into RE parallel with R pi into RE parallel with R pi. Whenever you want to calculate the output resistance, your voltage sources should be shorted. Voltage sources should be shorted, right? So R naught plus 1 plus GMR naught into RE parallel with R pi. So now this is node 1. From 1 to ground, you can have Rx. And here there is RC. So what is the output resistance R naught? The output resistance R naught is going to be Rx parallel with RC. The output resistance R naught is going to be Rx parallel with RC, right? And what is Rx? R naught plus 1 plus GMR naught into RE parallel with R pi. But if it is a MOSFET, you don't have R pi is infinite. So this is R01, this is R02. Of course, this is also a gate problem. And in future, I'm going to call this as a cascode amplifier. I'm going to call this as a cascode. It's a combination of common emitter with common base. And what will we do to the V bias? All the DC bias points are connected to ground. So what is R naught? So this is equivalent to a transistor with a resistance of R02. Here we have R01. So what is R naught? R naught equal to R01 plus 1 plus GM1 R01 into R02 into R02. So this is the answer, but examiner, this is R01 plus R02 plus GM1 R01 R02. Now, what is mega ohms multiplied by mega ohms? Mega ohms multiplied by mega ohms, that's a very big value. So this is approximated to GM1 R01 into R02. Otherwise, this is the exact value. This is the exact value. And this is the approximate GM1 R01 into R02. Now, this is for MOSFET. This is for MOSFET. But here we have this extra thing, right? The examiner gave in MOSFET. So there's an extra here. Who is this guy? R pi 1. So what should I write here? R02 parallel with R pi 1. It's R02 parallel with R pi 1. Then what is the best approximation for this? This is the approximation for MOSFET. What is the best approximation for this? Who is larger, R0 or R pi? R pi is larger. So it is R01 plus R pi 1 plus GM1 R01 R pi 1. What is R pi? Beta by GM. Beta beta gets cancelled. So this is R01 plus beta R01. This is neglected. So beta is very large. This is approximately beta R01. Like that also you can write. Right? Otherwise, this is the correct one. So you just expanded R02 parallel with R01, R02 parallel with R pi 1 is R pi 1. So this is approximated to R pi 1. Because mega ohms parallel with kilo ohms, it's kilo ohms. So then you start substituting. I've done for MOSFET. So MOSFET is there in my mind. Okay. So in the next topic, when we take up MOSFET, CB, CE, CC, common drain, common gate, and common source amplifiers, then I will do this once again for MOSFET. For BJT, it is beta times of R01. Now, how are we going to do this? Till here, we have already done for Q2. This is R03. This is R02. This is R pi 2. So till here, this is Rx. So what is Rx here? Rx. Rx is going to be R02 plus 1 plus GM2 R02 into R03 parallel with R pi 2. R03 parallel with R pi 2. Now, this whole the two transistors are now replaced by Rx. The two transistors are now going to be replaced by Rx. So we'll have Rx here. And this is Q1. Q1. Now here you're going to have R pi 1. So this whole thing is now going to be Rx. Rx. So again, what is R0 here? R0. R0 is going to be R01 plus 1 plus GM1 R01 into Rx parallel with R pi 1. So now you understand, how difficult it is getting where if you pile up more transistors, definitely the output resistance will increase, but doing by the small signal model is the most foolish thing to do, right? Because the upper transistor has got 1, 2, and then 3 loops here, 3 loops, 3 loops. So you will have 9 loops to solve. So you will have 9 loops to solve. So it's better we do by this method, right? So your R0 is going to be this value. And in the place of Rx, you have to substitute this value. In the place of Rx, you have to substitute this value, right? Now, this is the load I told you. This is approximated to 1 by GM2 parallel with R pi 2. It is 1 by GM2 parallel with R pi 2. And here you have R pi 1. This is your R01. So what is R0? R0 is going to be R01 plus 1 plus GM1 R01 into, these two are in parallel, 1 by GM2 parallel with R pi 2 parallel with R pi 1. So this is the reason mostly the early effect is neglected in GATE exam, right? But okay, even if he considers also, we have a way to do it. Now similarly, I want to remove this transistor, and this is my node 1, right? What is the resistance seen through base terminal here? The resistance seen through base terminal is R pi. From this node 1 to ground, it's R pi. Or if I take Q1 and Q2, it is R pi 2. I like this problem because the R pi 2 and the R pi 1 are going to come in parallel now. So what is R naught? It is R01 plus 1 plus GM1 R01 into R pi 2 parallel with R pi 1. It is R pi 2 parallel with R pi 1. Okay. Now I want node 1 here. What is the resistance seen through emitter? The resistance seen through base is R pi, but the resistance seen through emitter is alpha by Gm. So what is R naught here? R naught is going to be R01 plus 1 plus GM1 R01 into alpha by GM2 parallel with R pi 1. Alpha by GM2 parallel with R pi 1. Okay. So what is the voltage gain of this problem with without early effect? First we'll do without early effect and then with early effect, right? So what is V naught by V? This ground for AC analysis. So V naught by V says that there should be a negative sign. Imagine the collector current at the output and the collector current here, right? So if you imagine collector current in the numerator and the collector current in the denominator, the ratio of voltages is going to be the ratio of resistors, right? So what should I write in the numerator? RC, am I right? In the denominator, V in is VB. What is VB? 1 by GM. Am I right? Simple. So your V naught by V in is going to be minus GM into RC. Minus GM into RC. So this is something we have done if your early voltage is infinite. Your early voltage is infinite. Now we have to consider this extra R naught here. This extra R naught. And this node is ground. When this node is ground, this is some X here. From X to ground, there is R naught. From X to ground, there is RC. That means this R0 and RC are in parallel. This R0 and RC are in parallel. That we can see here in the first problem. So yeah, this is the circuit, right? This R0 and RC, the first problem, if you can see, the R0 and RC are in parallel. They are in parallel. So in the place of RC, what you can write in the place of RC? You can write RC parallel R0. Or you can do one problem by the small signal here. Here you have R0, base, emitter, collector. And from collector to ground, there is RC. And this is your GMVB. So your V0 is going to be minus GMVB times of R0 parallel with RC. And your Vin is VB. So what is AV? AV V0 by Vin is going to be what? Minus of something by something. If there is an early voltage, it is not equal to infinite, then in the place of RC, can you see RC here? In the place of RC, you have to write RC parallel R0 by 1 by GM. So what are you writing in the numerator and what are you writing in the denominator? In the numerator, you are writing the output resistance. And in the denominator, you are writing the total transconductance of the amplifier. So another way of calculating voltage gain is what? Output resistance divided by transconductance. Or rather divided by the inverse of transconductance. Because resistance by resistance is gain. So the 1 by GM is inverse of the transconductance. That becomes minus GM into, what is the answer here? This becomes minus GM into RC parallel R0. RC parallel R0. But whereas here, it is minus GM RC. Now it is minus GM into RC parallel R0 is the gain of the amplifier. So what? After early effect, what did we do? We extra R0 we are going to include in parallel with RC. That's all, right? Wherever RC is there, in parallel with RC, you have to put one extra R0. So instead of minus GMRC, you're going to get minus GMRC parallel with R0, right? So your V0 by Vin is going to be minus GM into R0 parallel with RC. This is by the small signal, Okay. Now, what happens if RC is infinite? What happens if RC is infinite? If RC is infinite, you can simply say V0 by Vin, which is minus GM into RC parallel with R0, is nothing but minus GM R0. Minus GM into R0. This we can solve it by small signal because only transistor is there, no resistors. Here you have Vin. Here you have Vin. And this is GMVB in parallel with R0. This is VB. So what is V0? V0 is going to be minus, this current is in the opposite, minus GMVB into R0. And Vin is directly VB. So from here, what is AV? Minus GM into R0. So this minus GM R0, it's got its implication. This is very, very important. Minus GM R0 is the maximum gain that you can get in BJT. Because when you connect the load and the load comes in parallel, naturally the gain will reduce. So you should always, a designer should always aim for this value. So what is the maximum gain you can get from a common emitter? It is minus GM into R0 of the transistor. And once you connect the load, then naturally the gain is going to reduce from this value. This is called the intrinsic gain. It is called the intrinsic gain, or rather the maximum gain that you can get from a BJT, right? But once you connect RL, naturally the gain will keep on reducing. So that is why a transistor load should be another transistor. So this is a current source. Can you see here? And how do you get a current source? This is another BJT circuit. So this is another BJT circuit. So that is why passive resistors are useless. Passive resistors, if you connect, the gain will reduce, right? They are only for discrete. Once you go for integrated circuit, all these current sources are nothing but another BJT. So if you connect another BJT here, then you're going to get huge gain, right? And the maximum gain that you can get is the intrinsic gain minus GMR naught. It is minus GMR naught. So this is the common emitter, and this is the common collector amplifier, CC. See, some students are saying that there is some background sound that is coming. Is it true? Are you getting some sound? There's nothing here. Only me. Nobody's there. Are you getting any sound? Background sound? Any sound? I was told some sound was there. Is it okay? Okay. So what about the common collector amplifier without early effect? What is AV? Without early effect, V0 by Vin. I told you, numerator some resistors and denominator some resistors. What are you going to connect? The numerator is going to be, this is an emitter resistor, so you can divide by alpha. And in this loop, Re by alpha plus 1 by Gm, which is nothing but you can have Re by Re plus alpha by Gm, like this. Or if you don't like, I told you, you can replace the BJT with the Thevenin equivalent. This is better. So what is the Thevenin equivalent here? It is a voltage source in series with resistance. What is the resistance seen here? It is alpha by Gm, right? Now here you can connect Re. Here you can connect Re, and you can get it. Yeah, I forgot. But what happens if there is early effect? If there is early effect, you will have an R0 here. Am I right? This is ground. And how is R0 and Re? Both are in parallel. So you can include R0 here also. So this way you can get the gain, V0. V0. And one more thing, what is the output resistance of the amplifier R0? Output resistance R0. For calculating output resistance, the voltage source should be short. Then all three are in parallel. Alpha by Gm parallel with Re parallel with R0, like that. Right? So at this node, see, there are three ways to reach ground. So for calculating output resistance, your voltage source should be shorted. Then from here, you have alpha by Gm, there's Re and there is R0. So it's something like this node 1. There is an Re here. There is R0 here. And because of the transistor here, there is alpha by Gm. I think it's better you draw the voltage divider, right? So if you draw the voltage divider, it's much simpler. So most of the gate problems, there is no early effect. So you don't have to worry when it comes to BJT. For MOSFET, we will definitely include R0. For MOSFET, R0 is important. But for BJT, already RPi is there, GM. So the analysis is getting bigger and bigger. So mostly early effect is eliminated and is avoided in BJT circuits for gate exam. So here RC is infinite. In the place of RC, in the previous case, it is minus GM into RC. Now it is minus GM into RC parallel with R0, right? Now please tell me the current source here. I told you there's a current source. The current source is another BJT circuit. But what is the name of this terminal? That name of the terminal is important, right? If you know the name of the terminal, then you can solve it. If you don't know the name of the terminal, then you don't know whether it's R pi or alpha by GM or R0. R pi is at base, alpha by GM is at emitter, R0 is at collector. So you should know the name of the terminal. So what is the name of the terminal here? It's collector. So the resistance here from here to ground is going to be R0, not R pi. So the same transistor circuit is drawn here, and here this is R02. So this is the common emitter. So what is the gain of this amplifier? V0 by Vin is going to be minus of output resistance by the transconductance, right? So what is the output resistance here? This is going to be R01 parallel with R02 by 1 by GM, or minus GM into GM1 into R01 parallel with R02. Minus GMRC, generally it is minus GMRC. If you have R0, it is RC parallel with R0. If RC is infinite, it is only R0. If there is another R0 in the place of RC, then it is R01 parallel with R02. It is R01 parallel with R02. Now what about this? This is a diode. This is a diode here. And a diode, you can treat it, this one as a load. And what is the value of load? It is 1 by GM2 parallel with R02. This is V. So what is V0 by V? V0 by V is going to be minus GM1 into RC. What is RC? 1 by GM1, GM2 parallel with R02. And of course, this one also has R01, so you can have parallel with R01. So it is minus GM1 into 1 by GM2 parallel with R02 parallel with R01. I think this is a gate problem, but instead of PNP, that is also NPN. Just tell me what is the best approximation in this gate problem, right? No small signal model, nothing. This is given for 2 marks. 1 by GM is tens of ohms. R02, R01 are in mega ohms. Mega ohms parallel with tens of ohms is tens of ohms. So it is minus GM into 1 by GM. And the examiner said both transistors have the same transconductance. So GM gets cancelled. The gain is minus 1. The gain of this amplifier is going to be minus 1. Because R02, R01 are in mega ohms. Mega ohms parallel with ohms, right? I think I've given you here today in the start. So this is important. Please see here. This is important. R0 is in mega ohms. Alpha by GM is in tens of ohms. R pi is in kilo ohms. R pi is beta by GM. Is it not? Beta by GM. So it is 100 times more. R pi is 100 times more than alpha by GM. And R0 is in mega ohms. So you do one thing, directly write the gain without early effect, and finally include that R0 in parallel. That's all, right? Include that R0 in parallel. For example, minus GMRC is a gain. In the place of RC, you write RC parallel with R0. Then you will realize that RC parallel R0 is actually the output resistance of the amplifier. It is actually the output resistance of the amplifier. So now you can take screenshots here. See here, all of you, here I made a mistake, right? It's a good catch. One of the student mentioned in the comments that it is 1 by GM parallel with what? This is 1 by GM parallel with R pi, is it not? Good catch. Is 1 by GM parallel with R pi. I wrote instead of R pi, I wrote R naught, right? And you will realize why did I write R naught in a short while. Okay, 1 by GM parallel with R pi, 2 parallel with R naught. So you can take screenshots now. Okay, so now before I go for MOSFET, common base, common drain, common gate, and common gate, common drain, and common source. What is the summary here? Summary. So first I included a C amplifier. In a C amplifier, for all these amplifiers, I will include source resistance, RS, and consider early effect also. Early effect, right? Source resistance, RS. So a quick review, summary here, V naught. So tell me, what is the input resistance of this amplifier? Input resistance, Rin. Rin is going to be Rs plus R pi. The resistance seen through base is R pi. What is the output resistance of the amplifier? The output resistance of the amplifier is RC parallel with R naught. And what is the voltage gain of the amplifier? The voltage gain of this amplifier is output resistance by the transconductance, right? So what is the output resistance? Output resistance by the input loop, whatever it is. What is the input loop here? 1 by GM plus RS divided by beta, am I right? What is the output resistance seen from here? Previously it was RC, now it is RC parallel with R naught by 1 by GM plus RS divided by beta. So yesterday we didn't had R naught, now we are including R naught, an extra R naught, which is included with RC, right? RC parallel with R naught by 1 by GM plus RS divided by beta, right? If there is an emitter resistor, what will you do? If there is an emitter resistor, then you are going to include whom? Emitter resistor divided by alpha. Base resistances are divided by beta. So this is the summary of what amplifier? C amplifier. So without early effect, we have already done so many times. So with early effect, I am doing it as a summary. Please, if you don't want early effect, what you have to do? If you don't want to consider early effect, then substitute R naught equal to what? Infinite. Then substitute R naught equal to infinite. We don't want early effect. What about common collector amplifier? Common collector amplifier. include RS also. So what is Rin? Rin is, if you see from here, from the input here, it is Rs plus R5 plus 1 plus beta times of Re. Rs plus R5 plus 1 plus beta times of Re. What about the voltage gain AV? V0 by Vin. First we'll write without early effect. Without early effect, it is Re by alpha by Re by alpha plus like that, or directly you can imagine numerator and denominator emitter current also can do Re by Re plus alpha by Gm plus Rs divided by 1 plus beta. This is numerator emitter current, denominator emitter current. Otherwise, numerator collector current, denominator collector current you want, then Re by alpha plus 1 by Gm plus Rs divided by beta. Like that also you can do. This is in terms of IE. This is in terms of IC. And what about the output resistance R0? The output resistance R0 is, I will shift this slightly here. Here you can see Rs. What is the resistance here? This is in parallel with Re. Am I right? So the resistance here is alpha by Gm plus Rs divided by 1 plus beta. This whole resistance is in parallel with Re. Is in parallel. Oh, we have to include this fellow also, no? R0. Now you can have R0 also. Right? Alpha by Gm plus Rs divided by 1 plus beta parallel with Re. Parallel with R0. See, already the gain is 1. For that, this mega ohm, there is no need. Is it not? It's very, very small. See, what is the value of R0 we got? 24 ohms we got. Right? What is 24 ohms parallel with mega ohm? Right? So don't be too perfect. Right? Even the examiner feels, include R0. How can he say? He cannot say because 24 ohms parallel with mega ohms is always 24 ohms. Right? Okay. This Re, if I remember, it was 8K, and alpha by Gm was around 26 ohms. So in parallel with it, we got around 24 point something. And now R0 has come with mega ohm. So don't worry about that, right? This is CC amplifier. What about CB amplifier? Common base summary. In a common base amplifier with source resistance. Now, what is the input resistance seen here at the emitter terminal from this node to ground? From this node to ground, it is alpha by Gm. So it is Rs plus alpha by Gm. Otherwise, if Rs is not there, just imagine Rs is not there. What is the input resistance? If Rs is not there, it is alpha by Gm. Now Rs is in series, so it is Rs plus alpha by Gm. What is the output resistance of this amplifier here? Oh, this is huge output resistance. If you see from here, the output resistance is, let me draw it like this. For calculating output resistance, voltage source should be shorted. And this RC is here, ground. And you have to include here, this one. So when you see here, these two are in parallel. So this is something we have already done. So what is output resistance of this amplifier? It is RC parallel with, this R0 plus 1 plus Gm R0 into Rs parallel with R5. Oh my God, see, so huge. This is approximately RC. Right? This is approximately 100% it is RC only, right? There is no need. Now what is the voltage gain AV? The voltage gain AV is, without early effect, you have RC by Rs by alpha plus 1 by Gm. RC by Rs plus alpha with 1 by Gm. If you want early effect, then the numerator should be output resistance. It is RC parallel with the whole thing, R naught plus 1 plus 2. Oh my God. There's no need for you to include early effect here. It's huge. Include early effect only for what? For calculating output resistance, right? When the amplifiers are in cascode. But if you do everything with early effect, it's getting huge. So I think this is enough. I think this you are comfortable with. Enough. Yesterday we have done this also. RC by emitter resistances are divided by alpha, base resistance are divided by beta. RS by alpha plus 1 by J, right? This is enough. So what is the easy way of doing early effect? First you write without early effect, and this RC is just coming in parallel with R naught. So you have to just include RC parallel with R naught, right? So from now onwards, things are much, much easier, right? And out of the three configurations, which one gives you negative sign? Which one gives you negative sign out of the three configurations? Only C, right? So the only C is going to give you negative sign. No other configuration is going to give you negative sign. Okay. So this is all about CB, CE, and CC with early effect also. Now, what is the small signal model? For MOSFET. What is the small signal model for MOSFET? In a MOSFET, we are little relieved because the gate current is 0. So there is no element here. This is gate, source, and drain. Now only two fluctuations. One is ID and VGS. The other one is ID and VDS. The other one is ID and VDS, right? Okay. So what is the fluctuation between ID and VGS? The fluctuation between ID and VGS, right? So defining transconductance. The transconductance GM is nothing but change in ID by small id by small VGS, which is change in ID, delta ID, right? DID by DVGS. DID by DVGS, right? So what is DID by DVGS? ID equal to mu Cox W by L into VGS minus VT whole square by 2. From here, what is GM? Change in ID by change in VGS. So if you differentiate, you get mu Cox W by L. Differentiation of x squared by 2 is x VGS minus VT. So this is GM. So what is GM? It is change in ID by change in VGS. All right. And this is nothing but the slope. This is nothing but the slope of the characteristic. So you can take VGS on x-axis, ID here. Suppose you are operating at this point, then that is the slope, right? So if you apply a small signal, this is the gain you get. This is small VGS, delta VGS, this is delta ID. And what is the value of GM, right? Delta ID by delta VGS. It is nothing but mu Cox W by L into VGS minus VT. And this VGS is from DC analysis. Is from DC analysis. So that is GM, transconductance. And what is the fluctuation between ID and VDS? ID and VDS. Small letters, right? Small letters, small letters. Small letters, ID and VDS. This is similar to the early effect. So if you want to know the slope, then you have to extrapolate. I told you it will intersect at a point called the early voltage. So what is the value of R naught? The value of R naught is going to be delta VDS by delta ID, right? ID, which is small VDS by small ID. This is nothing but the early voltage divided by capital ID. Early voltage divided by capital ID. So this is R naught. Now these fluctuations, we are going to model it now. The slopes we are going to model. The gate current is 0. So this is similar to an open circuit. Open circuit. Why open circuit? Because the current is 0. This is gate. And here you have the slope, so we can have some Norton equivalent, I told you, right? So you can have some Norton equivalent of the BJT. Oh, sorry, MOSFET. What is Norton equivalent? The Norton equivalent says that for this you have to short circuit here. This is ISC. And the output resistance is the short circuited resistance, RSC. This ISC is opposite to ID. This is ID here. So this is similar to VGS and the short circuited current ISC parallel with RSC. This ISC is nothing but minus ID. And what is ID? ID is What is ID here? ID GM equal to ID by VGS. So what is ID? ID is GM times of VGS. It is GM times of VGS. So this is GM times of VGS. And what is the short circuited resistance here between VDS and ID? This is R0. So how do you remove the negative sign? To remove the negative sign, the model is VGS. We will change the arrow. The arrow will put it down. GM VGS in parallel with R0. So this is the small signal model. Small signal model. This is the small signal model. At the input, what is the Norton equivalent for the input? Current is zero. Current is zero. That means it is open circuit. That's all, right? But the Norton equivalent at the output is a short circuited current in parallel with the resistance. Short circuited current is nothing but the minus of ID, right? So that is the reason we have to flip that sign now, and the arrow should point down GMVGS in parallel with R0. And what is GM for BJT? Note. What is GM for BJT? It is small IC by small VB. It is nothing but IC/DC by VT. It is IC/DC by VT. All right. But VT is not threshold. It is the thermal voltage, right? 25 millivolt or 26 millivolt. But what is VT in a MOSFET here? That is the threshold voltage. That is the threshold voltage. So just to show the difference of VT here, I've written it, right? Now, how many rules a BJT had? A BJT had 6 rules, out of which 2 rules are related with beta, right? If you go here, it is 1 plus beta times. So now, out of 6, 2 are going to be missing, right? Why? Because beta is infinite for MOSFET. The gate current is 0. If the gate current is 0, IB is 0. Something like you have a transistor with IB 0. If you have IB 0, then your beta is infinite. So there's no question of multiplication factor. So that way, it boils down to only 4 rules, right? Okay. So what is the resistance? reflection rule. What is the resistance reflection rule for MOSFET? The resistance reflection rule is rule 1. The gate current is 0. The gate current here is 0. So the rule 1 says that the resistance here is infinite. If you see through gate terminal, whether there is a source resistance, there is no source resistance, there is a drain resistance, it doesn't matter. The gate current is 0. So the resistance through gate terminal is infinite, right? So suppose you want to find the input resistance of CE amplifier. And the moment you see through gate is simply infinite, that's all. Now there is no drain current, source current separately, because if collector current, if base current is 0, then by Kirchhoff's law, collector current plus base current is emitter current. Collector current plus base current is emitter current, and base current is 0. So collector current will be emitter current. So your drain current and your source current both are same. So MOSFET, that way is very simple. There is only a single current, right? There is only a single current. So rule 1, there is no multiplication factor. Rule 2 says that. So what is in MOSFET, what is beta? Beta for MOSFET is infinite and alpha is 1, right? So beta is not there, beta is infinite and your alpha is 1. So now tell me, what is the resistance seen through emitter now? This resistance is going to be 1 by Gm. 1 by Gm. Why is it not alpha by Gm? Because alpha is 1 for MOSFET. Alpha is 1. And is there any multiplication factor? Suppose if I put a resistor through gate terminal. In a BJT, you are dividing it by beta, but beta is infinite. Beta is what? Infinite. So there is no multiplication factor. First of all, there is no current in gate terminal. Even if you put a resistor, it doesn't matter. So I think we have only 3 rules, right? This is not at all a rule. First one is not at all a rule. Second one, okay, 1 by Gm. The third rule says that this resistance is R0. The resistance here is going to be R0, right? And that's it. There is nothing is there in MOSFET. Fourth rule, yeah. Fourth rule is there. What is the resistance here? If you see here, it is going to be R0 plus 1 plus Gm R0 into R. 1 plus Gm R0 into R. Of course, fifth one is the diode. Here the input resistance is going to be 1 by Gm parallel with R0. That is why I wrote R0 there, because MOSFET is there in my mind. Today we have to start MOSFET, right? So that's running there in the background for me. Instead of writing R pi, R0, I wrote R pi, sorry, instead of writing R pi, I wrote R0 there. So it's 1 by Gm parallel with R0, right? So what is the proof for this? You want a proof for this, you can do. Here you have VGS. I'll make it V pi instead of VGS. This is Gm VGS parallel with R0. Now you want to calculate the resistance, and the gate and the drain terminal are shorted. Shorted. Apply a voltage V, find current I. Am I right? So what is V? V equal to V pi. What is I? I equal to Gm V pi plus V pi by R0. So what is V by I? V by I, if you do 1 by Gm, so that is 1 by Gm parallel with R0. So you do V by I, you get 1 by Gm parallel with R0. It's 1 by Gm plus 1 by R0. So it's going to be 1 by Gm parallel with R0. So let me put a box here. This is not at all a rule, so simple. And Rin through the emitter terminal, we have alpha by Gm. Here it is 1 by Gm. Here we have R naught. If you have a diode, you can write 1 by Gm parallel with R naught. And here it is R naught plus 1 plus Gm R naught, right? See, now you understand why did I put 1 by Gm parallel R naught in MOSFET here. In BJT, I would have written alpha by Gm. Instead of 1 by Gm parallel R pi, 1 by Gm parallel R pi, it's alpha by Gm only. But I want you to write 1 by Gm parallel with R pi. Why? Because in MOSFET, it's going to be 1 by Gm parallel with R naught. So your mind, now it's easy for your mind, right? If you have a BJT, you'll write 1 by Gm parallel with R pi. In a MOSFET, you'll write 1 by Gm parallel with R naught. But you and I know that it is approximated to 1 by Gm only. It is approximated to 1 by Gm because 1 by Gm is very, very small. 10 ohms parallel with mega ohm, right? So we are trying to be too perfect here. 10 ohms parallel with mega ohms is always mega ohms, right? Okay. You can take a screenshot if you want. Okay. So first we'll do the common source amplifier. Common source is similar to common emitter. Common source is similar to common emitter, right? find AV. So these are all different types of common source amplifiers. This is a gate problem. Now, after finding AV, we will calculate R naught. And Rin, I told you, is waste of time. Rin, if you see through gate terminal, the current is 0, so the resistance is infinite. So there is no point in finding, right? Just find AV. So now the things will go much faster. And once we finish this configurations, we can go for differential amplifier. In differential amplifier, that is the only topic where probably the answers of BJT and the answers of MOSFET are going to be same, exactly same, right? There's no difference in the analysis. So the values are same. So when you realize that, then it's better, right? Okay, so these are different common emitter or common source amplifiers. Okay, so we'll start. Tell me. So V naught by Vin, imagine a single current. Sorry, there is no need to imagine. There is already a single current in a MOSFET. That is, whether you like it or not, only one current will flow. Yes or no? So if a single current is flowing here and here, then what is VGS? Your VGS is going to be, what is VGS? VGS is equal to ID into 1 by GM. Your VGS is going to be ID into 1 by GM, right? So this is ground and here you have ID. So what is V naught? V naught is minus ID into RD. V naught is minus ID into RD and your Vin is VGS. Vin is VGS. So what is V naught by Vin? V naught by Vin is minus ID by VGS into RD. And what is ID by VGS? It is GM minus GMRD. Minus GMRD. So this is a proof, right? What is the intuitive way of solving it? The intuitive way of solving is, I told you, you just have to write V naught by Vin with a negative sign and some brackets like this, right? Right? In what you call the numerator, the current ID is flowing through RD, so you will write RD here. And at the input loop, you have VGS, so you write 1 by GM. Am I right? So this is eliminating what effect? Early effect, right? But if you have early effect, then I told you, you have to include R naught. And R naught comes in parallel with what? RD. So you have to just put R naught here. So what is the answer? Minus GM times of RD parallel with R naught. RD parallel with R naught. So this is without early effect. This is with early effect. Are you getting? Or if you want to do by small signal, V pi, GM V pi in parallel with R naught, in parallel with RD. So now your V naught is going to be minus GM V pi. V pi is Vin. V pi is nothing but Vin. Vin times of R naught parallel with RD. So your V naught by Vin is going to be minus GM into R naught parallel with RD. Okay. Now, the good thing about MOSFET is you can directly write V naught by Vin. Suppose I take some node Vx here. You can directly write V naught by Vin as V naught by Vx into Vx by Vin. Now, how can we directly write it without any loading, nothing? Because the current here is zero. The current here is zero. So it's almost like an open switch here. You can imagine an open switch. So this device is voltage controlled. So your V naught by Vx you can do separately, and your Vx by Vn you can do separately. What is V naught by Vx? V naught by Vx is minus GMRD. Or here it is RD parallel with R naught. What is Vx by Vn? This is Vx. What is Vx by Vn by voltage division? It is R2 by R1 plus R2. It is R2 by R1 plus R2 is your Vx by Vn, right? It is minus GM into RD parallel R0 or RD. If he says R0 is infinite, it's minus GM RD into R2 by R1 plus R2. See, my suggestion is, whenever passive elements, resistors are given, don't consider R0, because if you don't consider R0, the value is almost same. But when is R0 important is, a transistor is connected with another transistor as a load. If the load is another transistor where RD is not there, but a small R0 is there, then you cannot neglect R0. This R0, see here, instead of RD parallel with R0, can you see RD parallel with R0 here? Instead of that, if you have R0 parallel with R0, then you cannot neglect, no? The R0 parallel with R0 is R0 by 2. You cannot neglect. But if generally passive resistors are there, there is no need for you to consider R0. Okay. What about this? We know that this is ground for AC analysis. So what is the AC equivalent? This is RS. Here we have R1 parallel with R2. This is almost like an open switch, is it not? You can do it orally, but I'm just writing it. What is V0 by Vs? It is V0 by Vx into Vx by Vs. Am I right? What is V0 by Vs? Imagine a single current. There's no need to imagine. You can simply write minus Rd by, what will you write in the denominator? Please see here, there is no alpha here. There is no alpha, emitter resistor by alpha, base resistance by beta, nothing, just Rs you have to write. Plus 1 by Gm. Very, MOSFET is very easy. Minus Rd by Rs plus 1 by Gm. And what is Vx? What is Vx by Vs by voltage division? It is R1 parallel with R2 by R1 parallel with R2 plus Rs. R1 parallel with R2 by R1 parallel with R2 plus Rs. So this is V0 by Vs. If you want, you can include R0 also. Then what is R0? R0 plus 1 plus GM R0 into Rs will come in parallel. That's a headache. A small resistance in parallel with a large resistance is going to be small. So this is okay, isn't it? So this I'm calling it MOSFET 1 and MOSFET 2. Now what is MOSFET 2? This one is going to be 1 by GM2 parallel with R02. It is going to be 1 by GM2 parallel with R02. And I told you this is a gate problem. 1 by GM2 parallel with R02. So imagine a single current. Don't include early effect first, right? Just imagine a single current and put a negative sign bracket in here. Now, who are the resistors at V0? V0 is the voltage across this 1 by GM2 parallel with R02. Right? In the input loop, you have VDS. So Vin equal to VDS. Wherever VDS is there, 1 by GM. 1 by GM. All right. Now, if you want to include R0, then this R0 is going to be in parallel with that. So you can have this. But you know what is the headache? In gate exam, he said there is no R0. And both MOSFETs have the same transconductor. It is given for 2 marks. So there is no R0 in gate problem, and both MOSFETs have same transconductance. So it is minus 1 by GM by 1 by GM. So 2 marks questions will be like this, minus 1. Are you getting? There is no question of any R0 there. Yeah. Now, what do you mean by V bias? V bias means this is connected to ground for AC analysis. Whenever the gate terminal and the source terminal are grounded, both are grounded, it's not a diode. When is it a diode? Only when the base terminal and the collector terminal or the gate terminal and drain terminal are shorted, then it is a diode. So tell me, what is the name of this terminal? It's called drain. So that means there is an R0 from here to ground. There is an R0 from here to ground. M1 and take M2, R02. So now you can have R02 here, V in, V0. So what is V0 by V in? We have already done this. It is minus GM1 times of R02. R02, but here there is an additional R01. R02 parallel with R01. So now you cannot neglect R0 because both are R0s, right? R parallel R is R by 2. So it is minus GM RC. In common emitter, this was minus GM into RC parallel R0, right? It is RC parallel R0. Now it is minus GM into R02 parallel with R01. So this way we can avoid a small signal. But please, anytime you have an element of doubt, then please do by small signal. The problem is, on the first day when I've done with small signal, 3 problems we have done. CB, CE, CC. I can see, if maybe I'm not physically observing you, but from the comments I can see that you are literally tired. You don't want to apply Kirchhoff's law. Every time you want shortcut, right? So any complicated problem, a student expects me to do it half a page, right? So within this half page, he wants me to finish, right? It could be a 5 transistor, 10 transistor process. So in such an occasion, if I keep on writing Kirchhoff's law, you'll get worried. But if you have a doubt, please, you have to practice. Yes or no? When you do that, and then you come back here, you will enjoy it, right? So please, if you have some element of doubt, how this is happening, what is it intuitively, you have to cross check with, what you call the small signal, right? Always you should have more than one method in hand, is it not? Whenever you want to crack an entrance exam, to arrive at the solution, you should always have one method extra, right? There's always a tool. Okay. So this is the intrinsic gain. It's minus GMR0. Your RD is infinite, is it not? Your RD is infinite. So what is V0 by V in? Is going to be minus GM into RD parallel with R0. But your RD is infinite. So this is going to be minus GMR0, intrinsic gain, right? What is the proof for it? Of course, this proof we can do by small signal because there is only one MOSFET, nothing is there. So here you have V pi. This is GM V pi in parallel with R0. In parallel with R0. And the source terminal is grounded. Input is given here. Output is taken here. Am I right? So such problems, even by small signal, it takes the same time, right? So what is V in? V in is V pi. What is V0? Minus GM V pi into R0. And V in is V pi. So what is V0 by V in? V0 by V in from here, V0 by V in is going to be minus GMR0, which is the maximum gain you can get in a MOSFET, the intrinsic gain. Okay. Yeah. Now you can see in this problem, both gate terminals are shorted, both drain terminals are shorted, and source terminals are connected to ground. So this is like two MOSFETs in parallel, right? This is a MOSFET. And now I have another MOSFET, which is a PNP. I can convert it into an NPN because same terminals are there. It is something like this, right? And of course they are shorted, so you can draw like this also, right? This is just a way to show that both gate terminal are shorted. Now what is the small signal model of this? Small signal model of two MOSFETs in parallel. Two MOSFETs in parallel. Two MOSFETs in parallel, or we can have even MOS BJT also. So if you have two MOSFETs in parallel, then we can have a Vpi here. GM1 Vpi in parallel with R0. Now what about the second MOSFET? The second MOSFET is going to have one more here, GM2 Vpi in parallel with R0 or R02. Now, if two current sources are in parallel, there is the same node, both have the same gate, both have the same source, both have the same drain. So if two resistors are in parallel, what is the overall resistance? If two current sources are in parallel, what is the overall current source, right? So the total GM, two current sources are in parallel, the overall current source is addition, GM1 plus GM2. And what is R0 of the total is going to be R01 parallel with R02. Right? So if both have same transconductance, this is 2 times of GM. This is going to be R0 by 2. It is going to be what? R0 by 2. Now, what happens if two BJTs are in parallel? If two BJTs are in parallel, then you will get an extra R pi, that's all. GM, there's R pi here, R pi 1. Here there is R0. Now here you're going to have R pi 2 because same terminals, GM2 Vpi, Vpi, and here another R0, is R01, R02. So what is R pi total? It is R pi by 2, is it not? It is R pi 1 plus R pi 2. What is GM, R pi 1 parallel with R pi 2? R0 total, R01 parallel with R02. If both are same, it is R0 by 2. And GM total is going to be GM1 plus GM2. Both current sources are in parallel, addition, 2 GM. So the transconductance is going to get 2 times, the resistance is going to get half, and the GM is going to get doubled, right? Now on the same token, see here, the two transistors, what is the other way of drawing two transistors? You can draw a transistor and you can put two arrows like this. This is a lazy way, but it is a good way, is it not? Instead of drawing the whole MOSFET, all the number of lines, just put two arrows. So this circuit is nothing but MOSFET with two arrows. And here you have V0. This is V. So just now we have done this, the current source, yeah. Can you see the sixth problem? The sixth problem and seventh problem, both are same. Both are same. Here current source has infinite resistance and there is nothing there. So it is infinite. So both look same, but the only difference is the transconductance is 2 times and the output resistance is half. So what is V naught for this problem? V naught for this one is going to be minus of GM1 plus GM2 into R01 parallel with R02. And how did I get this answer? From here, this one. Can you see from here? Here, single MOSFET, we are getting minus GM-R0. Two MOSFETs is going to be GM1 plus GM2 into R01 parallel R02. What happens if three MOSFETs are in parallel? It is GM1 plus GM2 plus GM3 into R01 parallel with R02 parallel with R03. Now, what if N MOSFETs are there? N MOSFETs. Then GM1 up to GMN and R01 parallel with R02 up to R0N. And if all MOSFETs are same, and there are N MOSFETs, all MOSFETs are similar and they are N MOSFETs, then your total GM is going to be N GM and R0 is going to be R0 by N. So N gets cancelled. It is finally GM R0 only. So even if you have 1000 MOSFETs in parallel, and if they all have the same transconductance, the gain is still going to be same, right? But of course, the output resistance is going to decrease. The total R0 is going to be R0 by N. The output resistance is going to get divided by the number of MOSFETs, right? Okay. Okay, so we'll do one thing. I'll now give you few questions and we'll take a break. After the break, I will solve. So the first configuration we have done is a common source. Now we'll see the other two configurations. I'll just give you questions. You just note down, right? Or you can take a snapshot of that and we'll take a break. And then when we come back, we will solve them, right? So just note down the questions. So we have done the common source amplifier. So what are the other two configurations? We can have the common gate amplifier, right? What is the number? I don't know the number. Let's start again with 1. the common drain amplifier. See, like this, we can create so many, right? There's no limit. Or in the same problem, we can have a common drain or common source, both. It all depends on where you take the output, is it not? So where you take the output, suppose you want V01 by Vin and V02 by Vin. In the same problem, right, where will you get phase shift and where will you not get phase shift, you can decide, right? Okay, so we'll take a break. You just take a snapshot and try. After the break, we will do it. And then once we are done with all this, we can go to a fresh topic called the differential amplifier. Very, very important, is it not? Because you can see that the examiner in the new syllabus is very clearly mentioning differential amplifier and current mirrors. So he's very specifically mentioning that, right? Okay, we'll take a break. Okay. Are you able to hear? Can you hear me? So let's get started. This is a common gate amplifier. In a common gate, input is given at source, output is taken at drain. Am I right? So for calculating voltage gain, you have to imagine a single current. I told you, if it is a BJT, emitter resistors are divided by alpha and base resistors are divided by beta. But here nothing is there. There's only one current. So you have to just write the resistors. That's it. So what is V0 by V? V0 by V is some resistors in the numerator and some resistors in the denominator. When you apply Kirchhoff's law, what is the resistor for V0? So you have RD here. And V in, there is VGS. So VGS is GM times of, or ID by VGS is GM. So VGS, I can write it 1 by GM. V in equal to VGS. So this is going to be plus GM into RD. So wherever VGS is there, please write 1 by GM. Wherever VGS is there, please write 1 by GM, right? So it is plus GM into RD. Now, please, you can always neglect R0. You can always neglect R0 if you have passive resistors like this. But please don't neglect R0 if you have what you call, if you have active elements, active load. This is a passive load. This is a passive load. In the place of a passive load, if you have another MOSFET, then you should never neglect the value of R0. Is it not? Okay, so this is plus GM into RD. What about here? V0 by Vs is going to be, tell me, what is V0 by Vs? Numerator, what resistors, and denominator, what resistors. In the numerator, you have RD. In the denominator, in this loop, you have RS and then 1 by GM. So this is going to be the gain of the amplifier. RD by RS plus 1 by GM. But if you want to include R0, there's a big value. R0 plus 1 plus GM R0 into RS, so it's not needed, right? That will come in parallel with RD, right? Now, here, you cannot neglect the effect of R0 here. Can you see here? There is an active load. This is called the active load. What do you mean by an active load? A transistor, if it is used as a load, it is called what? An active load. So here you cannot neglect the effect of R0, right? So now here you have suppose this is M1 and M2. So you have R02 here. Okay. V in. So what is V0 by V in? V0 by V in is going to be, in the numerator, you have R02. In the denominator in this loop, you have 1 by GM. 1 by GM, it is going, or GM1, it is going to be GM1 into R02. GM1 into R02. But what is the output resistance seen from here when you short the voltage source? What is the output resistance seen from here when you short the voltage source? Here you are going to have R01 also. So that R01 is going to come in parallel. It's going to come in parallel. So it is R02 parallel with R01. It is R02 parallel with R01, right? And the denominator, you will have transconductance. In the numerator, you will have the output resistance of the device. So the output resistance when the V in is shorted is going to be R02 parallel with R01. Now, what about this? In this problem, you can totally neglect R1 and R2. Why you can neglect R1 and R2? Because the gate current is zero. The gate current is zero, and this is your V bias point, the DC bias. This bias point is 0 volts for AC analysis. For AC analysis. So even if there is some DC voltage there, when you draw the AC equivalent, it looks like the previous problem. So this is a bias point. So what is V0 by Vs? It is RD by Rs plus 1 by Gm. RD by Rs plus 1 by Gm, right? Now tell me, now this is equivalent to, here you are going to have R02, and this is 1 by Gm3 parallel with R03. So what is V0 by Vin? V0 by Vin, without early effect of M1, it is going to be R02 parallel with 1 by Gm3 parallel with R03. Am I right? And in the denominator, you are going to have 1 by Gm1. But now there is an early effect even in the first transistor. So when you calculate the output resistance, this is the output resistance. In the output resistance, this resistor is also going to come in parallel. So it's 1 by R02 parallel with 1 by Gm3 parallel with R03 parallel with R01 by 1 by Gm1. So this is going to be the voltage gain. Now tell me what is V0 by V in here without early effect. What are the resistors in the numerator and denominator? It is Rs. In this loop, it is Rs plus VGS is there 1 by Gm. So wherever VGS is there, you have to write 1 by Gm. But if you include early effect, then it is Rs by Rs plus 1 by Gm. If you include early effect, then you have an extra R naught coming into picture. You can write it parallel. But as I told you, if there are passive elements, then please neglect the R naught. It is not needed. Examiner also will not ask. But when is R naught very important is, if the load is also an active load, then R naught is very important, right? Now the first problem and the second problem, both are same. Let us draw a NPN equivalent for this. Before that, we have to draw AC equivalent. Am I right? So from the source to ground, there is RS, where you take the output. The drain is connected to ground, this drain, source, and input is given to V. So this problem and the first problem both are same. So V naught by V in is going to be Rs by Rs plus 1 by Gm. If you include R naught, then Rs parallel with R naught. So what you write in the numerator is the output resistance. What you write in the denominator is the transconductance of the amplifier. The overall transconductance of the amplifier is what we write in the denominator. What we write in the numerator is the output resistance of the amplifier. That is why the gain in general is Gm into Rc. What is Gm? Transconductance. Rc is the output resistance. So in general, your V naught by V in is going to be minus of total transconductance. Now this one we'll take it to the numerator, the denominator, sorry, into the output resistance. So this is going to be minus of Gm total into R out, output resistance, right? What is Gm total here? In the above case, what is Gm total? 1 by Rs plus 1 by Gm. 1 by Rs plus 1 by Gm. Your Gm total is going to be 1 by Rs plus 1 by Gm. Is that total transconductance? So what we write in the denominator is the short circuit transconductance. What we write in the numerator is the output resistance of the amplifier. So in some gate problems, the examiner asks what is the short circuit transconductance. Then whatever comes in the input loop, that you write with a 1 by whatever comes in the input loop. If you write, you get the short circuit transconductance. So this is the output resistance, Rs. And if you include here one more R naught, then you can have Rs parallel with R naught also, right? Okay. So here Gm total, you can have minus sign, because minus of minus is plus, right? Minus of 1 by Rs plus 1 by Gm. This is common base, no? Common base or common drain. This is common drain, no? Yeah, common drain. Okay. What about here? This whole thing is going to be 1 by Gm2 parallel with R02. So what is V naught by V? What you are going to write in numerator and denominator. In numerator, it is 1 by Gm2 parallel with R02. In denominator, 1 by Gm2 parallel with R02 plus this VGS is here, right? 1 by Gm1. 1 by Gm1. But if you have early effect, then you will have parallel with R01. You can have wherever 1 by Gm2 parallel with R02 is there, you can write parallel with R01. Or what you call the Thevenin equivalent for this? You will have 1 by Gm And here you can have 1 by GM2 parallel with R02. And this R01 also is in parallel. You can take like this and you can apply voltage division, right? And here you can take Vx. Oh, what is the gain of this amplifier? V0 by Vs is going to be V0 by Vx into Vx by Vs. V0 by Vx is Rs by Rs plus 1 by Gm. And Vx by Vs, this R1 is going to come in parallel. R1 parallel R2 by R1 parallel R2 plus Rs. Please draw the AC equivalent for it, you will know, right? Now what about this? Here we have R03. This is 1 by GM4 parallel with R04. This is R03 here. This is again 1 by GM2 parallel with R02. Now out of these two, who will give phase shift and who will not give phase shift? If you do V01 by Vin, input is at gate, output is at drain. It's like common emitter, V01. So definitely there will be a negative sign. It is R03 parallel with 1 by GM4 parallel with R04. By input loop, you're going to have 1 by GM1 plus 1 by GM2 parallel with R02. This is V01 by Vin. What is V02 by Vin? V02 by Vin is numerator is 1 by GM2 parallel with R02 by 1 by GM2 parallel with R02 plus R01 plus R01, right? Again, you don't have to include the resistance in the opposite and all that, not needed, right? 1 by GM2 parallel with R02 by 1 by GM2 parallel with R02 plus 1 by GM1. So the denominator for both are same because V in loop is same. The denominator for V01 by Vin and V02 by Vin both are same. The denominator is going to be same. Okay. Now for common base amplifier, for common emitter amplifier or common source amplifier, I have not found the input resistance because the current through gate is zero. So if the current through gate is zero, then the resistance is infinite. There is nothing to find there, is it not? So now voltage gain we have found. Yeah, this problem I was telling you is given in GATE exam. And see here, it is given for 1 mark. So now you can imagine the GATE examiner is also thinking that you should not do by small signal model. If you do by small signal model, definitely this can be treated like an 8-mark question or something like that, R naught plus 1 plus GM R naught. But why he has given for 1 mark? 1 mark he has given, right? That means he wants you to do it intuitively. Are you getting right? If you want to do it by bookish method, okay, you can do it, but time consuming, that's all, right? You can always cross check. So this is a GATE problem for 1 mark. He said, what is the output resistance? Calculate the output resistance. So what are the important parameters in an amplifier? I told you, calculating the gain, calculating input and output resistance. One is the strength of an amplifier. The second one is the impedance matching. And the last one is the tau and bandwidth. So tau and bandwidth. Okay. This is R naught. So what is R naught? It is small R naught parallel with RD. What about here? R naught is going to be R01 plus 1 plus GM1 R01 into R02. There is no R pi, right? So this is R01 plus R02 plus GM1 R01 R02. This is approximately GM1 R01 R02. So this is given for 1 mark in the exam. But if you do by small signal model, it looks a little cumbersome, right? So what is the resistance here? Rx. Rx is going to be R02 plus 1 plus GM2 R02 into R03. Into R03. Am I right? So this is equal to approximately GM2 R02 R03. GM2 R02 R03. So now you have Rx here. This is M1 R01. So what is R0? It is R01 plus 1 plus GM1 R01 into Rx. What is Rx? Rx is Rx. GM2 R02 R03. Then this is approximately what value? GM1 GM2 into R01 R02 R03. GM1 GM2 R01 R02 R03. So like that you can pile up, right? If 2 are there, it is GM1 R01 R02. If 3 are there, GM1 GM2 R01 R02 R03. If 4 are there, GM1 GM2 now you know, right, the pattern that moves. But can we do this by small signal? Because each transistor will have 2 loops. So 6 loops will be there in the small signal model. It is difficult to do, right? Now tell me, what is the name of this terminal? What is the name of this terminal? If I put node 1, the name of this terminal is source. So what is the resistance seen here? The resistance seen here is 1 by GM. It's 1 by GM. So from this node to ground, you can have 1 by GM and R0. So your R0 is equal to R0 plus 1 plus GM1 R01 into 1 by GM2. Into 1 by GM2, right? Now, the resistance seen through emitter terminal is 1 by GM, irrespective of any load value. In fact, if you ask me strictly, this resistance is this actually. If you ask me strictly, the resistance seen here, if you go in the reverse direction, the multiplication factor for a common gate amplifier, it is something like this. Here you have R naught. So it is R naught plus RL by 1 plus GM R naught. This is a value you will get if you do by small signal. And what I am trying to say is, because this emitter terminal, your input resistance or output resistance is going to be 1 by GM. Now, if you ask me, how is it possible? Because small signal will give you this, but I am saying 1 by GM. We all know that R naught is in mega ohm, RL is in maybe kilo ohms, right, or ohms. Mega ohms plus this is R naught. And GM R naught is always much greater than 1. Much. This is a right, very big value. Suppose this is 5,000. Compared with 5,000, 1 is very small. GM R naught. Then your R naught will get cancelled. It is going to be 1 by GM. Okay, so the resistance seen through, even the resistance seen through a transistor here, we have written this as what? Alpha by GM. Alpha by GM. Here it is going to be 1 by GM. 1 by GM. But if you do by small signal strictly, it is going to be R naught plus RL by 1 plus GM R naught. But R naught is much greater than RL. GM R naught is far greater than 1. If you cancel, it is 1 by GM. So for MOSFET, it is 1 by GM. For BJT, it is going to be alpha by GM. And one more simple trick I'll tell you. The trick is, suppose the examiner has given all options, including with R naught. You substitute in those options R naught as infinite, you will get without R naught value. Yes or no? So you can crack. That is not a big thing. If we, because generally these type of questions, 4 options will be there. And you don't want to include R naught, don't include R naught, happily find. But in 4 options, you put R naught equal to infinite, divide numerator and denominator by that value, substitute infinite, you will get the answer. No? So you don't have to worry, right? Because this problem is a gate problem. But I keep telling students it is 1 by GM, but the gate examiner, he put small signal, everything R naught plus RL by 1 plus GM R naught. That value is also 1 by GM. So please substitute R naught equal to infinite here. You are going to get 1 by GM. So like this, it is not that you have to prove something in gate exam, right? Even in IES exam, this will work. Why? Because even before doing the problem, you already know the solution. Yes or no? And you can do some drama, apply KVL, KCL, this, that steps, and finally you can put this answer. Who will ask? Yes or no? So even without doing anything, by inspection, you know a 10 marks problem solution, a 15 marks problem solution. So when you already know the solution, you know how to get that, right? Suppose you don't know the solution, at least you know how to substitute. You can substitute R naught equal to infinite in the 4 options, you can get the answer. Yes or no? So don't worry about trying to be too perfect, right? So this is a what you call emitter terminal. Whenever you see through emitter, the resistance is going to be what? 1 by GM. Or strictly speaking, what is the resistance here? R naught plus RL by R naught plus R by 1 plus GM R naught. You have to write, but not needed. That value is approximately equal to 1 by GM. Okay. Fine. So like that, we can create so many questions. So what is the summary? Summary of common source, common gate, and common drain amplifier. Right? Intuitive. How do you spell intuitive? Okay. So first there is a common source amplifier. You want source resistance, you can take, but there is no current flow, so there is no point, is it not? So what is Rin? The gate current is 0. Rin is infinite. What is R0? R0 is RD parallel with this R0. And what is the voltage gain of a common source amplifier? Minus GMRD. Minus GMRD. Or if you include R0, is RD parallel R0. So this is the common source amplifier without a small signal model. Right? What about common gate amplifier? Now for complicating this, you can put a source resistance also. Then what is the input resistance of this amplifier? Here, Rin. Here we know, here it is 1 by GM, but now in series, your Rin is going to be Rs plus 1 by GM. And your R0 is going to be RD. Your R0 is going to be RD. But if you include early effect also, then it is RD parallel with R0 plus 1 plus GM R0 into Rs. Then what is the gain of the amplifier? The gain of the amplifier, it is going to be numerator, there is RD, denominator it is Rs plus 1 by GM. Rs plus 1 by GM. And don't put parallel R0 plus R. That's such a big value will be there. That in parallel with RD is almost going to be RD on, right? Is almost going to be RD. And please, what is current gain? Why I'm not mentioning current gain? Because load current and the source current are same. Only one current is flowing. So what current gain shall we create, right? So one and the same. And what is the last amplifier? Common source, common drain amplifier. Right? If you want, you can have the equivalent. Here, this is, what is the resistance here? 1 by GM. And this R0 is also, if you want, you can include it here. Now, what is the output resistance R0? What is Rin? Rin is infinite. Rin is infinite. How do you find output resistance? If you see here, you have to short the voltage source for output resistance. And it is 1 by GM parallel with R0, parallel with Rs. What is the voltage gain? Voltage gain by voltage division. These two are in parallel. So you can include like this, two resistors in parallel. 1 by GM. This is R0 parallel with Rs. This is our voltage division rule. What is voltage division rule? R2 by R1 plus R2. V0 by Vin is going to be R2 by R2 plus R1. R2 plus R1. Now tell me, compared with 1 by GM, this value is in kilo ohms, this is in ohms, is approximately 1. Is it not 0.9 like that you will get? So common drain amplifier is a voltage buffer. Common drain amplifier is a voltage buffer. And common gate amplifier, this is a current buffer. Current buffer. Because the current gain here is going to be IL by IL. What is IL and IN here? ID by ID. Yes or no? ID by ID is 1. So this is a current buffer. Now this fellow is a voltage buffer. Common drain amplifier is a voltage buffer. So common drain amplifier has high Rin and low R0. Common gate amplifier has low Rin and high R0. If you treat RD as the load, then look at the R0 offered by the BJT. R0 plus 1 plus GM R0, right? So one is a voltage buffer, the other one is a current buffer. Okay, right? Let us go for a fresh topic now. That is called what amplifier? Differential amplifier. Differential amplifier, right? A differential amplifier is a direct coupled amplifier. Direct coupled amplifier without capacitors. Without capacitors. It is a basic building block. It is a basic building block of analog IC design. It is a basic building block of analog IC design. I told you capacitors in the order of microfarad range is difficult to fabricate. Difficult to fabricate. Is difficult to fabricate, right? Now, then when it is difficult to fabricate, when you are drawing an amplifier, how you are eliminating capacitors, how to eliminate capacitors, right? How to eliminate capacitors. How to eliminate capacitors. Now, the first thing is the need for voltage divider and coupling capacitor is eliminated by biasing with negative supply. Negative supply. Now, in a differential amplifier, we are going to use negative voltage to a transistor. When you use negative voltage, when you use a negative voltage, still the diode is on because the cathode is connected to minus terminal. There is no need for you to put voltage divider and then block that 4 volt with a capacitor. No capacitor is needed at the input side. Now, bypass capacitor is also not needed. Bypass capacitor is not needed as the emitter terminal is at virtual ground. This we have to discuss, right? Virtual ground. When the emitter terminal is already grounded, there is no need for you to again extra connect a capacitor. Output capacitor is not needed as the DC is cancelled by differential measurement. Differential measurement. A differential amplifier, even in a small space, you are able to fabricate because all the 3 capacitors are no longer needed. Otherwise, I'll tell you, there was a time where there's a fight between analog and digital, right? Analog means what? It is the law of the world. You cannot talk digital, right? Voice, speech, video, audio, everything is analog in nature. So analog is like a crude form of electronics in those days. But suddenly digital came over, right? Digital was taking over because the processing is very fast in digital. But the real world is analog. The real world is analog. So there's nothing new that is happening in the field of analog. So most of the analog engineers, they felt that they will lose jobs, right? Analog is going to be an outdated field. Mostly analog to digital conversion. Some converters will be there. Rest else is digital. So people thought even analog circuits, all these circuits have capacitors, and they cannot come, in a miniature form, in an IC form. So they felt analog engineers are going to lose their jobs, right? In such a period, a group of guys, right, hustlers, you call them, and they sat together and they found a way out. They felt, yes, we are going to remove the capacitors even in the transistor circuit, because initially they tried, there's a technology called I think the planar technology. They bought the whole common emitter amplifier on a wafer of a very big size, but on such a big wafer, if one amplifier comes, it is waste, is it not? So we have to say that they were unsuccessful in bringing out the planar technology. But in monolithic technology, there is a possibility that you can fabricate transistors which are exactly same, exactly alike. Then they felt, yes, now we are able to, create an amplifier that is going to totally eliminate the need for what? Capacitors. How? Let's see. First, what is the need for this amplifier? Now, suppose you have a common emitter amplifier here. In a common emitter amplifier, I told you, this is IC, this is ground. What is V0? V0 is minus ICRC. And Vin is VB. Vin is VB. Vin is VB. Now, what is V0 by Vin? It is minus IC by VB into RC. And small change in IC by VB is GM. It is minus GM RC. This is a voltage gain. Now, what is the guarantee that you get a voltage gain like this? Suppose I give a sine wave like this, you have to get like this, right? You have to get like this. But do you think you can get like this? No. The reason is this VB is changing due to Vin, accepted, but the VB can also change due to temperature. And temperature is a common problem. It's a common mode devil. Noise is a common problem. Any unwanted thing is noise. The change in temperature is unwanted, so we call it as noise. Any noise is going to be an unwanted signal. So I don't want the variation of temperature, but there will be, right? When the temperature in a room changes, obviously, the circuit parameters are going to change, right? So this VB can also change due to temperature, and your output due to temperature, when that VB is changing due to temperature, that the wiggle that the temperature is going to generate, that is noise here. That is noise. So your output is going to be this in this fashion for an input signal of this. So this is getting superimposed. Then how do we eliminate noise? And this is a common problem. Common emitter is going to suffer, is going to cry because of the variations in temperature. Then they felt that why not draw the same common emitter amplifier 2 times, like 2 times. You have to draw the same common emitter amplifier 2 times, and here you're giving signal from base to ground. Here, why not give the signal between the 2 base terminals? Between the 2 base terminals. And here, this is the load RC here. Now, what happens if you give this Vin to 2 common emitter amplifiers? Both the common emitter amplifiers you have given. But you might say, okay, sir, there is an RPi here, and through this RPi, the complete VB was dropped. But now this Vin has got another RPi to get distributed. So this Vin can have to distribute through this R pi and this R pi. It's almost like you have what you call two resistors, and you applied a signal Vin with a common emitter here. This is a common emitter, and this is the base of the first transistor, base of the second transistor. Now this is going to behave like your center tap transformer. There's a common emitter, the common, right? The emitter is common. With respect to emitter, you have to talk. With respect to emitter, if this is Vin, this drop is Vin by 2. This drop is also Vin by 2. Vin by 2. Now you tell me, what is VBE? VBE of the first transistor, VBE1. VBE1 is going to be Vin by 2. What is VB2 of the second transistor? VB. See here, there's a negative, there's a plus here. Negative plus. VB. This is B and this is E. VBE is going to be minus Vin by 2. So this is a beauty. Noise will not know this trick. When you connect a signal as Vin, the amplifier is going to cut your signal into two parts, and half of the signal is going to have a positive waveform. The other half is going to have a negative waveform with a common emitter in the middle. It's almost like a seesaw where a kid is playing. Have you played seesaw in a park, right? So this is like this, right? If one guy goes up, the other guy comes down. If one is positive, the other is negative. So the wave that you are giving, you might give a sine wave like this. You might give a sine wave 2 sine t like this, 2 sine t. But on one end, there will be 1 sine t. On the other end, there is going to, if one waveform goes up, the other waveform is going to go down. If one waveform goes down, the other goes up. So at any instant of time, please see my hand here. It's going to be like this, right? So one goes up, the other comes down. One goes up. But noise is a common problem. It will come and attack same in Q1 and Q2. So what happens if there is a noise N here, there's a noise N here, and you take the difference? The common noise is just going to get cancelled. I'll show you how it is here. If this Vin is Vin by 2 here, and this is Vin by 2 here, with a common emitter here. And of course, don't worry about biasing. We can bias so many ways by current source. So I'm biasing by something, right? So don't worry about biasing here. Just see what is this VC1 here, and what is VC2 of this common emitter. You can see here, what is V0? V0 from here is going to be minus GMRC times of VB. Can you see here? V0 is going to be minus GMRC times of VB. Now, the same thing, what is VC1? VC1 is also going to be minus GMRC times of VB1. But what is VB1? It is minus GMRC times of Vin by 2. What is VC2? This is another common emitter amplifier. VC2 is again another common emitter amplifier. It is going to be minus GMRC times of VB2. But what is VB2? Because of the phase splitting here, if one end is positive, the other end is negative. So VB2, this is B, right? VB, can you see? VB. So VB means minus Vin by 2. So minus of minus is plus. It is plus GMRC Vin by 2. Now, look at the beauty now. What happens if you take difference between the two? Difference V0. If you take difference V0, then it is going to be VC1 minus VC2. This is minus GMRC Vin by 2 minus of plus GMRC Vin by 2. So this is going to be minus GMRC Vin. So the gain of common emitter amplifier and the gain of two common emitter amplifiers is same. There is no change in the gain. Whatever single transistor was giving, the same output the two transistor is also giving. Now you might ask, sir, why did we go for two transistor when the gain is same finally? This output is going to be signal plus noise. This output is going to be signal plus noise. But what happens here? This one is minus GMRC by 2 plus some noise N here, some noise N. This is going to be plus GMRC by 2 plus noise N. What happens when you take the difference? When you take the difference, you will get a signal output minus GMRC, but this here left side there is N, right side also there is N. The common noise is going to get what? Cancelled. So VC1 is going to be this plus noise. Of course, noise will always be there. Here also plus noise. So what will happen at the final output? The final output is free from noise. Final output. When you take difference VC1 minus VC2, the noise is going to get cancelled. Final output is free from noise. So if you want to eliminate noise, which is a common problem, then you have to fight by creating symmetry. That means you should have two transistors which are exactly alike. When monolithic technology came, the transistors was fabricated on layers, metal on one layer, diffusion on one layer. Then there is a possibility to create two transistors which are exactly same. Then they built the differential amplifier. They invited the common noise, just kicked it, right? When you take the difference, the common noise is simply going to get cancelled, right? So what analysis is this, DC or AC? This is AC analysis. Okay, so let me repeat this once again. Your V0 is minus GMRC times of VB, right? But VB can be Vin and VB can be temperature. So this is a practical problem. We might simply connect and think that my VB is changing only because of Vin, but VB can also change due to temperature. If VB is changing only due to Vin, you will have a signal like this. If VB is also changing due to temperature, it will be like this. When you add both of them, then you will have a signal over which there is superposition of noise. When you add a signal and noise, you will have something like this, right? So this is a terrible problem. Common emitter has to suffer. Then how we can eliminate the common problem? By symmetry. Now you draw two common emitter amplifiers, tie them to a common point here, and don't give a signal to base to ground, give it to between the two base terminals. If you give between two base terminals, not between base and emitter, then this signal has to get distributed to two transistors, and it's going to distribute as V in by 2 and V in by 2, right? So what is V naught or VC1? It is now again minus GMRC times of VB. But this VB, remember, this VB is going to be V in by 2 plus noise also, right? Some sort of a noise. So minus GMRC V in by 2 plus some factor N. You can take noise as N. What is VC2? VC2 is going to be again minus GMRC times of VB. What is VB here? What is VB here? VB is minus V in by 2. It is going to be minus V in by 2. So minus of minus plus. Now, what happens when you take differential measurement? If you take differential measurement, then whatever the noise is here at this point, the same noise is expected at this point. And the common noise is going to get cancelled. So the output is going to be free from noise, right? Okay, that's great. But what is the need for these capacitors? How did we eliminate the three capacitors? The output capacitor is not needed as the DC is cancelled by differential measurement. So what is the need for an output capacitor? If you do the DC analysis, for DC analysis, AC sources are grounded. This is I naught. Now tell me, this I naught is going to split as I naught by 2 and I naught by 2. Then what is VC1 and VC2? DC. VC1 DC is going to be VCC minus I naught by 2 into RC. What is VC2 DC? That is also same. VC2 DC is also the same thing. Then what is VC1 minus VC2, which is your V naught DC? If you take difference, the DC is 0. When the DC is 0, why you need an output capacitor? In a common emitter, what is happening in a common emitter here? In a common emitter amplifier, you have a coupling capacitor, bypass capacitor, and an output capacitor. What the output capacitor will do? What the output capacitor will do? Suppose there is 6 volt here. There is 6 volt. Here also there will be how much voltage? DC, 6 volt. 6 minus 6 is 0. But here, suppose you have 6 plus 0.2 sine omega t. Now, if I want only AC, then I have to connect a capacitor and block this 6. Now, there is no question of blocking. Just subtract 6 here, 6 here. 6 minus 6 is 0. Your V naught DC is 0, right? What is V naught total? By superposition, it is V naught DC plus V naught AC. V naught DC is 0. V naught AC is minus GMRC V in. So finally, your output is only AC output, only AC output. But here, to get only AC output, you have connected a capacitor. This capacitor is no longer needed, right? Okay. What about the second one or the first one? The first one is the need for voltage divider and the coupling capacitor is eliminated by biasing with a negative supply. What do you mean by that? The first, can you see here, this whole section is not needed now. Why it is not needed? Not needed. Why is it not needed? Because the main aim of connecting this is such that it will charge to 4 volt here and it will forward bias the diode. So to forward bias the diode, we are charging. For charging, we have put a capacitor. Now the point is, this diode is also on with a negative voltage. No? If I connect a minus VE here, can you see here there is a negative minus V? Yes or no? So if you connect here, there is no need of There is no need of what divider? Voltage divider and coupling capacitor. There is no need of voltage divider and coupling capacitor, right? So this whole section you can just eliminate because the diode is already on with a negative voltage. See, cathode, this cathode is connected to negative. If cathode is connected to negative, even if anode is grounded, the diode is on. So biasing is done here with a negative supply. There is no need of voltage divider, right? Now, what is the necessity of this capacitor? What is the necessity of this capacitor? You tell me. This capacitor is going to see that this emitter node is pulled down to ground. This should be at 0 volts, no? Now, can you see the seesaw here? The seesaw action. Suppose this is plus 2 volt here. This is minus 2 volt. Are you getting? So if one goes up, the other is coming down. Plus 2, minus 2, minus 2, plus 2. Now just tell me, if I have two resistors and this end and both are R pi, if one end is plus 2 volt, the other end is minus 2 volt, what is the common emitter in the middle? This simple network. This is virtually at 0 potential already. The emitter in the middle is already, why is it at 0? Because one end is going up, other end is coming down. Seesaw. Right? So the middle point is already at 0 potential. You don't need a bypass capacitor separately for a difference amp. Can you see here? This point is virtually at 0 potential, the common emitter, right? So DC current will flow, but AC, it is as good as there is no I naught at all. There is no I naught at all. It's like two individual amplifiers are there because one end goes up, the other end comes down. You can have a virtually this node as ground node and you can solve. See, simple. What do you mean by ground? Ground means a voltage that does not move, that does not change, is static. So one end goes up plus 2, minus 2, plus 5, minus 5. This point is static. It's as good as ground node, right? So this is virtually at 0 potential, right? One is plus 2, other one is minus 2. One is plus 5, the other one is minus 5. So when you don't, when this, see, but here, this is not at ground potential, right? This is not at ground potential. There is an RE here. And you have to bypass RE. To bypass RE, they have put a capacitor. Are you getting? But here, what they are doing, if you have a single transistor, see how great these analog guys, right? So if you put a resistor here, then this voltage cannot be 0. So you are putting a capacitor. What I'm trying to say is, if there is another symmetrical circuit like this, and if you connect a voltage between the 2 points, here, then if this is plus, this is minus, if this is plus, this is minus, this point is already at 0. This is, of course, ground is 0. Then there is no need for you to connect a capacitor. Whether you connect it or not, upper plate is at 0, lower plate is at 0. It's like I'm a fool if I connect it, right? Because the upper plate is experiencing 0 potential. The lower plate is also experiencing. So by symmetry, they were able to eliminate the need for bypass capacitor also. Output capacitor, of course, not needed because when you take difference, 6 volt cancel, noise, DC is cancelled, noise is cancelled, everything is cancelled. Only AC signal will be there, only AC, right? And voltage divider is not needed because you're biasing, the forward bias junction of the diode is on with a negative voltage. Okay. Now, method 2, if you draw AC equivalent, voltage sources, short circuit, current sources, open circuit, right? So the circuit will look like this. Here I am applying a signal. Now all of you, in a transistor, how many currents are flowing? There are 3 currents. But while writing voltage gain, we have imagined output loop as IC and input loop also as IC, as if there is only one current IC, right? Now, I am a little hasty now here. When a single transistor, you have 3 currents, you imagine one current. When there are 2 transistors, you have 6 currents. You have how many currents? 6 currents. But still, out of 6, we will imagine one current. What will happen if I imagine only one current here? See here, I imagine only one current. Here IC, here also IC. Then what is VC1? Tell me Ohm's law. If a current comes from ground, it is negative. If a current goes to ground, it is positive. If a current comes from ground, it is negative. Current goes to ground, positive. And wherever VB is there, I told you, you have to write 1 by Gm. Wherever VB is there, you have to write what? 1 by Gm, right? So tell me, what is VC1 by Vin directly? Directly. VC1 is a voltage across RC and the current is coming from ground minus RC by, in this loop, there are 2 VBs, VB, right? So it's 1 by Gm plus 1 by Gm. Because wherever VB is there, you'll write 1 by Gm. This is going to be minus Gm RC by 2. So this is exactly we got for the left side. What about the right side? VC2 by V. VC2 by V. Now, right side, if you see here, the current is going to ground. If the current goes to ground, V equal to IC into R, V equal to I into R. So you'll have RC by input loop VB, 1 by Gm plus 1 by Gm. So this is going to be GMRC by 2. GMRC by 2. So if VC1 by Vin is minus GMRC by 2, VC2 by Vin is plus GMRC by 2, what will happen if I take difference in the middle? If I take the difference, then V0 is going to be VC1 minus VC2, that is minus GMRC, minus GMRC. So we are imagining how many currents here? Only one current, IC here and IC here. Now you might say, sir, 3 transistors, IC is okay. Now, two transistors, 6 currents are there, but still you imagine only one current. Because, see, simple. In a single loop, how many currents will flow? Tell me. In a single loop, can I say this, here I'll have IE1, here I'll have IE2, and IE1 is minus of IE2, and then, see, this is a nonsense, is it not? Right? If you keep on naming IB1, IC1, IE1, IB2, IC2, IE2, and then this looks like a series circuit, and then there are what? 6 currents flowing, right? It's waste of time. Instead, if you imagine a single current, wherever VB is there, you have to write 1 by Gm, but 2 VBs are there. So it's 1 by Gm plus 1 by Gm. So left side it is minus GMRC by 2. Right side it is plus GMRC by 2. See, I was telling you that MOSFET and BJT, only for this topic, both are going to give same answers. Whether it is a BJT or a MOSFET, it doesn't matter. Both are going to give same answers. So, method 3, if you want, you can follow any one method, right? I'm just suppose the same signal is applied between two MOSFETs here. And V. Then how will you solve VD1 by V in and VD2 by V in? VD1 by V in and VD2 by V in. Suppose I take this as node 1. I take this as node 1. What is the resistance seen through emitter? What is the resistance seen through emitter? You can write the resistance seen through emitter or source terminal is 1 by GF. Here, this M1, this M1. Here you have RD, this V0. So what is V0 by V? V0 by V, which is, sorry, what is this? VD1, right? VD1 by V. Now this is like a common emitter amplifier. So a common emitter or a common source amplifier is going to give you 180 degrees phase shift. So it is minus RD by, in this loop there is VGS, so you will write 1 by GM plus again 1 by GM. So this is going to be minus GM RD by 2. This is going to be what? Minus GM RD by 2. Am I right? Now, if you want VD2 by V, VD2 by V, you can have a Thevenin here. You can have a Thevenin equivalent. What is the Thevenin equivalent of this? It is a voltage source V in series with resistance. What is the resistance here? 1 by GM. And this is given to the second BJT, MOSFET. This is M2. So now what is V0? This is a common gate amplifier. See, if I don't split it, if I keep on speaking, you will not know it. The right side is going to be the common gate amplifier. There is no phase shift, but the left one is a common source amplifier. So it is giving you phase shift. So what is VD2? What is VD2 by V? There is a common gate amplifier, which is M2 here. M2. This is M2. This is M2, right? Now tell me what is M2? M2 VD2 by V in is going to be RD by 1 by GM plus 1 by GM. It is going to be GM RD by 2. So the left one is always going to give you minus GM RD by 2. The right one is going to give you plus GM RD by 2, right? But the second method is simple, right? Just imagine one current. Wherever VB comes, just write 1 by GM, 1 by GM, right? Left side current is coming from ground, so it's negative. Right side current is going to ground, it's positive. So this is method 3. A MOSFET is also going to give you what? A MOSFET is also going to give you the same answer as the BJT, right? So M1 is a common source amplifier and M2 is what amplifier? A common gate amplifier, right? This is method 3. Any one method you can follow. The first method was simple mathematics, VB, IC by VB is GM, right? The second method, some logic we applied, we considered same current. The third method, we have split that amplifier as a common source left side and a common gate right side, right? Method 4. Method 4, if you want, you can use the small signal model. So what is a MOSFET or a BJT for that matter? A BJT is going to have R pi GMVB or V pi 1. This is V pi 1, Q1 transistor. And here, so I'm drawing two transistors separately, but before we connect the resistors, we have to name the terminals. Without naming the terminals, we don't know where to connect, right? So let's name the terminals. This is base terminal. This is emitter terminal. This is collector. This is base. This is emitter. This is collector. So we have drawn two transistors separately, right? Tell me in a differential amplifier, if two transistors are there, what should I do to both the base terminals? Both the base terminals, we have to give what? Vin. Vin. Emitter terminals you can short. Collector terminals, you can connect a resistor here, right? Collector terminals. And the supply is grounded. Here you can take the output. So here you have a loop here, right? Now, this is GMV pi. So this current is also going to be GMV pi 1. So this current is going to be GMV pi 2. All right. Now give me a KVL in this loop. KVL. Give me a KVL there. We'll go like this. GM V pi 2 is a current into RC minus V naught minus GM V pi 1 into RC equal to 0. Equal to 0. So what is V naught? V naught is going to be, what is V naught here? Minus GMRC into V pi 1 minus V pi 2. V pi 1 minus V pi 2 minus GMRC into V pi 1 minus V pi 2. This is equation 1. Now give me a KVL in this loop, one more KVL here. In this loop, minus V in plus V pi 1 minus V pi 2 equal to 0. So V pi 1 minus V pi 2 is actually your V in. So substitute 2 in 1, what do you get? Your V naught is going to be minus GMRC times of V in. So the gain of common emitter and the gain of two common emitters both are same, right? V naught is minus GMRC times of V in. So my favorite out of these four is, these are not my favorite, right? My favorite is just see and write. So that means method 5, where you don't do anything, right? A good analog engineer should never do anything, right? You should just, by inspection, you have to solve. So method 5 tells that if there is symmetry, symmetry means what? Q1 transistor is equal to Q2, M1 equal to M2, right? RC, RC, RD, RD, everything is same. If there is symmetry, then the gain of half circuit is equal to the gain of full circuit. So what do you mean by this? This is a very powerful statement here. The gain of half circuit. That means when you take half circuit, you will completely give full signal to it. Aadha circuit, pura signal. You take half circuit and give full signal. But when you say gain of full circuit is same, when the gain of full, you give half signal to each. So full circuit with half signal is same as half circuit with full signal, because there's only one signal. So instead of drawing the whole circuit, half circuit you have to draw. What is half of the BJT? It is only this. This point is at virtual ground. We'll make this as ground node. Ground node. This RC P0. So anytime they give you a MOSFET amplifier, you can draw like this. And this V naught is going to be VC1 minus VC2. It is going to be what? VC1 minus V2. And what is V in? Please see here, what is V in? It is V pi 1 minus V pi 2. Or if you separately give V in 1, V in 2 also, it is V in 1 minus V in 2. If separately you give V in 1 to left side, V in 2 to right side, it is the same thing. V in 1 minus V in 2 is V in. VC1 minus VC2 is V naught. In such an occasion, why we have to do 2 times? Yes or no? Minus x by 2 plus x by 2, then difference is minus x by 2 minus of minus plus x by 2 is minus x. So you want minus GMRC, why you have to do half aadha left side, aadha right side, and then take the difference? Instead, you take half circuit, the gain of half is the gain of full. So now tell me, what is V naught by V? V naught by V in is going to be minus RC by 1 by GM. It is minus GMRC, minus GMRC. But if you ask me what is V naught, it is VC1 minus VC2. What is V in? V pi 1 minus V pi 2. So you can connect V in 1 here, V in 2 here, V in 1 minus V in 2. So I like this. That means don't do anything, take other circuit, and whatever the half circuit gain is there, the full circuit is also going to give you the same gain. But you can play this only when there is a symmetry. Of course, differential amplifier should have symmetry, is it not? So the gain of full and the gain of half both are same. Are you getting? So by looking at this circuit, without doing left side, right side, just by taking the half circuit, just tell me the answer. Find the differential gain. V naught by V. When I say V naught by V in, it means it is VC1 or VD1 minus VD2 by V in 1 minus V in 2. It's one and the same, right? Just take half and tell the answer. Just draw half circuit and tell the answer. Find the differential gain V naught by V. Or you can take V in 1 here and V in 2 here. It's one and the same. What do you mean by symmetry? M1 equal to M2, M3 equal to M4. M1 equal to M2, M3 equal to M4, right? So how V in 1 minus V in 2 is V in? Suppose this is gate 1, G1. This is G2. Previously, I have given between G1 and G2. This is G1, G2. Here I am giving V in, right, in the previous problems. In this problem, I am giving V in 1 from here to ground, V in 2 from here to ground. So, this is V in 1 from here to ground. This is V in 2 from here to ground. So now you can apply KVL. You can apply KVL to know the relation. Minus V in 1 plus V in 2 equal to 0. KVL. Your V in equal to V in 1 minus V in 2. Right? You can apply KVL here. What do you get? Minus V in 1. Give me KVL. Minus V in 1 plus V in 2 equal to 0. Or V in equal to V in 1 minus V in 2. So it's one and the same whether you say V in 1 minus V in 2 or this is one and the same, right? So you take half circuit and just tell the answer. Just Adha circuit you draw and tell the answer. The gain of Adha circuit is the gain of Pura circuit. Half circuit gain and the full circuit gain both are going to be same, right? Okay. So we'll solve this. So we have 10 minutes to go and we have 5 problems. So we'll take 2 minutes per problem, right? 2 minutes for each problem and finish it. So let me repeat, the gain of half circuit is equal to the gain of full circuit. Am I right? The gain of half circuit is equal to the gain of full. Now tell me, if this gate terminal and this gate terminal, if one end goes up, the other end comes down, where is the virtual ground? Because if you know the virtual ground, then you can cut the amplifier into 2 parts, right? If this end goes up, this end comes down, then this middle point is point P here is at virtual ground. If one end goes up, the other end comes down, right? Symmetry. So you can cut, that's the line of symmetry there, right? This is of course ground. So the line of symmetry says that point P is at virtual ground, is at virtual ground. So let me draw half circuit here. So now tell me, what is V naught by V? Minus of something by something, am I right? So what is that something? Resistor at the output RD. At the input you have RS plus, and if you want you can divide by alpha. What is alpha? Alpha is 1. In a MOSFET alpha is 1, right? So RS plus 1 by GM. So this is the differential gain. This is the differential gain, right? Half of it will be left side. The other half of it in the positive without phase shift you will have in the right side, right? Because the examiner wants differential measurement, gain of half circuit is equal to gain of full. Okay. So shall we go for, yeah. So with explanation, 2 minutes, right? In half minute you can solve it. We can take 2 minutes for explanation also, right? We'll go for the next one, right? So what is the gain of half circuit? The gain of half circuit, this is point P. The point P is at virtual ground, V in and V naught. M3, what is M3 here? 1 by GM3 parallel with R03. Am I right? This is M1. So what is V naught by V? V naught by V in is going to be minus of something by something. So what are the resistors in the output loop there? It is 1 by GM3 parallel with R03. And the resistors in the input loop 1 by GM1. But I told you, you should not neglect, you should never neglect R0 if there is an active load here. There's an active load. So this R01 is going to come in parallel with that. Is going to come in parallel with that factor. Wherever 1 by GM3 parallel with R03 is there, extra R01 you have to connect, right? So this is the differential gain of 4 transistor amplifier by intuition, right? Otherwise, imagine drawing these 4 using the small signal model. Just imagine drawing the 4 using the small signal model, right? Obviously, you will get a wrong answer. Right? The reason being, if the number of steps are more, then naturally you're bound to make mistake somewhere, right? Yeah. So this one is simpler. We have already done this. Gain of half circuit is equal to the gain of full, but this point P is at virtual ground. Point P is at virtual ground. So your V in and here the V naught, right? So what is the gain of this common emitter amplifier or common source? V naught by V in, we know that it is going to be minus GM into R naught parallel with RD, right? What is RD here? RD is infinite, right? Infinite. So it's minus GM R naught, minus GM1. So the same problem you can do even by small signal like this. So here you have GM V pi, this V pi here, and here you have R naught here, right? So the same problem we can do by 2 methods also, this V in Am I right? So what is V naught? V naught is going to be minus Gm R naught V pi. And what is V in? V in is V pi. So if you divide it, you get minus Gm into R naught. Okay. Yeah, I think close to 2 minutes. Now, what about this? Where is the line of symmetry here? Tell me, where is the line of symmetry? If one end goes up, the other end comes down. This guy goes up, this guy comes down, this guy goes up, this guy comes down. Where is the line of symmetry? The line of symmetry says that this resistor should be cut into two parts. How can you cut the resistor into two parts? If you have a 1 kilo ohm, you have to write it as two 500 ohms in series, right? And then the middle point will definitely be at what ground? Virtual ground. So let me draw the AC equivalent. The AC equivalent says that current sources are open circuit. So I'm writing two resistors here. This is RDD by 2. This is RDD by 2. And here you have RSS by 2 and RSS by 2. And now this is your V in 1 and V in 2. Now tell me, when you apply the common V in, this V in 1 with respect to the emitter is going up, the other one comes down. When this end goes up and this end comes down, what will happen? The point P here is going to be at virtual ground. Is going to be at what ground? Virtual ground, right? So other circuit, half circuit is this virtual ground, virtual ground. Right? So V naught by V in is nothing but VD1 minus VD2 by V in 1 minus V in 2. Now tell me, minus of something by something. What will you write in the numerator and what will you write in the denominator? Numerator, it's RDT by 2. Denominator, you're going to write RSS by 2 plus 1 by G. So this is the gain of the differential gain of this amplifier, right? Okay. So half circuit, this is point P here. And what is the name of this terminal? Drain. So drain means you'll have R03. This is point P. So what is V naught by V? This is the common source amplifier, GM1 into R03. Here you have a R01, it's parallel with R01. Minus GMRC, is it not? So if R naught is in mega ohm, right? So you can imagine the amount of gain that you get in these amplifiers, right? That is why even a two-stage amplifier with active load, even a two-stage amplifier, differential amplifier is going to give you a gain of 10 lakhs in op-amp. Op-amp gain is 10 lakhs. It's not because there are so many stages. Two stages is enough. Why? Because you should not use passive load. You have to use active load. You get R naught. R naught is in mega ohm. So tremendous gain you get even if there are two stages, right? Okay. And take a screenshot. Yeah, 6:30. So we come to an end of today, right? And Okay, so we'll have some question and answer session. You can ask question answers. Venkat, question answers. Yeah,
Hello, sir. Good evening, sir.
yes,
Sir, can you go to 18F?
18F. Yeah,
Sir, why on right side RD is infinity, sir?
current source. No? Current source means what? What is a current source? A current source is one whose output resistance is infinite.
Infinite.
That is why whenever you are doing Thevenin's equivalent resistance, you have to open circuit current source and short circuit voltage source.
Voltage source. Okay, sir. Sir, another 26F, sir. Sir, here on the first question, we have 1 plus GM R naught, no, sir. 1 plus GM.
Here only R naught is there, no? Where is there is no resistor in the emitter, no?
Oh,
This is V pi. This is your GM V pi. And here you have R naught. And here you have RD.
whenever there is an emitter resistance, then only we need to consider.
Multiplication factor will be there. Nothing is there, no? Okay, you can do like R naught plus 1 plus GM R naught into 0 you can do. Here you can see 0, no?
Yes, sir.
So you can put 0 there. R naught plus 1 plus GM R naught into 0.
Yes. Sir, another doubt, sir. Sir, can you go to resistance reflection rule for MOSFET, sir?
Yeah, page.
I didn't remember the page number, sir.
Yeah. This one, huh?
No, sir. 5 rules you told us, sir.
Yeah.
Fifth rule, yes, sir. Sir, here in fifth rule, R in equal to 1 by GM parallel in R naught, na, sir. This R naught means when we are shorting a drain and source, that R naught and this R naught on same, sir.
No, R naught is the dynamic resistance, no? Between drain and source, yes.
Sir,
This
but we are
small signal model already has R naught, no? This one.
Yes, sir.
This R naught only.
In BJT, we are connecting collector to the emitter.
Yeah, here also we are connecting collector to emitter, we are connecting. Yeah, this one is collector only, no? Gate, source, drain. Between drain and source, we are connecting.
not. Okay, sir. But here we are shorting drain and gate, na, sir, in fifth rule.
Yeah, this here you are shorting. That is why GM V pi, voltage is V pi, so it is giving 1 by GM, this current source here.
Yes, sir.
This is R naught, 1 by GM parallel with R naught.
R naught. Okay, sir. Okay, sir. Thank you, sir.
Okay. Next.
Hello,
sir. 25F, sir. Hello, sir.
25, sir. Hello. Hello, sir.
Yeah.
Sir, 25.
Yes.
Sir, here 25. I think 24.
Okay.
Sir, this one is sir. 25 only, sir. Sir, here at M1 VO2, we didn't given feedback, no, sir. Then why 1 by GM to parallel to RO2?
No, this is a diode, no? This is called the drain terminal. This is called the gate terminal. When drain and gate are shorted, it is something like this. This is called the gate terminal. This is called the drain terminal. You have shorted. That means it's a diode, no?
Okay, sir. I got confused as you didn't connect it.
Yeah, I mean, they are little far. Huh? You have to put one line like this.
Okay, sir.
Yeah.
Hello, sir.
Yes.
Sir, I'm Sahil Suman speaking.
Yeah, tell me.
So I had a doubt in which a lot of times when we are taking out A, you just there was a rule which was saying that take minus and then put bracket for taking out A.
Yeah, that is
And
only
then
for common source and common emitter. Only common source or common emitter will have negative sign. And upper bracket is for output loop. Lower bracket is for input loop. Whatever the resistors at the output loop, you have to put in upper bracket. Whatever the resistors at input loop, you have to put in lower bracket.
okay, so that was only I was like a lot of question, a lot of parts you didn't consider the minus. That was only when to take which ones. Just
No. Only when input is given at base, output is taken at collector, there should be a minus sign.
okay,
Or
sir.
input is given at gate, output is taken at drain. There is a minus sign. In any, see, for example, you can see here, input is given at gate. Can you see the first problem?
Yes, sir.
Output is taken at source. This is a common drain or common collector. So here there won't be any negative sign. Negative sign is only for common source amplifiers.
Okay, sir.
The first amplifiers we have seen only are common source. Those amplifiers you can take negative signs.
Okay, sir.
Here you can see all are common emitters only. Negative sign, all are common emitter or common source. There's a negative. Can you see a negative here?
Yes, sir.
Because input is here, output is here. What is your doubt there? Why this negative?
No, sir. Where should we take the negative and not to take the negative?
That's what. Only for common source and common emitter, we have to take negative.
Okay, that was only my doubt.
Okay.
Thank you, sir.
Right.
Hello, good evening, sir.
Good evening.
Sir, could you open 35F, sir?
Yeah.
Sir, I understood the last 2 points of the capacitor one, but sir, input capacitor at negative supply, you told that I could not get, sir.
Yeah. For a transistor to be on,
Yes, sir.
The base emitter junction should be forward bias. This one. This is a transistor. To make it on, the base emitter junction should be forward bias. This should be forward. Now you have two ways. One is you can give 4 volt here and ground.
Okay.
Second way, you can give ground here and -4 here.
Okay.
So to give 4 here and ground here, they went for voltage divider. Before the 1960s, they had a voltage divider. And to block that voltage, they put a capacitor. And this capacitor was charging to 4 and it was forward biasing this junction. So they have used this for so many years. But suddenly they wanted this circuit on integrated circuit, finished. They could not.
Okay.
Then they felt, what is the necessity? The necessity is, this is forward biasing diode. Can't we forward bias this with a negative voltage here, -4?
Okay.
Are you getting?
Okay, sir, means this is the -V at the emitter terminal which we use.
Minus, see, same current will flow. See here. For example, there is 3.3K here. 3.3K. This is ground. Here it is 4. Tell me what is the current? 4 minus 0.7. 3.3. 3.3 by 3.3, 1 million.
Yes, sir.
Yeah. Now we will do one thing. I will give -4 here. 3.3. And I will ground this.
Okay.
Now this will be -0.7. Then the current is going to be -0.7 minus of -4 by 3.3K. It is again 1 million.
Yes, sir.
Are you getting?
Yes, sir. So second,
diode is
sir,
on.
second, one more doubt, sir.
What?
Sir, one more doubt. Could you open 27F, sir?
Sure. Why not? Yeah.
Sir, here this minor doubt, sir. RX we are looking from the top side. So
Yes.
it should be at the drain terminal of this. No, sir, we are connecting at source terminal.
Yeah. First you can see from here. But that is only R03. What
Yes,
is there
sir.
to see?
Yes,
Then
sir.
we went up. That is RX. Then there is R0.
Oh, sorry, sir. I numbered in the opposite way. Okay, okay. Sorry, sir.
Very good, very good. Now you got it, no? That is
Yes, sir,
important.
yes,
Why
got it.
sorry? The main aim is you have to understand that, sir. Yes or no?
Yes, sir. Yes, sir.
Yeah,
Got it.
yeah. Good, good.
Thank you very much, sir.
Okay, okay. Next. Next.
Hello, sir.
Hello.
Yes.
Hello.
Hello, sir.
Good evening, sir.
Yeah.
So my doubt is in 10F.
Yeah.
So here, why did we consider R pi
Where is R pi?
while we were calculating R naught? Second line.
This one,
Hmm.
here we have, this is a BJT, no? This R pi will come in parallel with RS, I told you.
Okay, it's the BJT wala problem.
ये BJT वाला है. This is common base.
Okay.
Okay, good, good.
And sir, 33F.
हाँ.
See here, my connection was lost. Can you please explain whatever happened
Yeah,
here?
see, a single common emitter amplifier will have signal as well as noise because your VB is also changing due to temperature.
Hmm.
But if you invite the same change noise here at this point, can you see here? Noise N and same noise N if it exists at another common emitter. These are two common emitter amplifiers.
Hmm.
But here you are taking difference, no?
Hmm.
Take difference, the common noise is going to get cancelled. That is the main idea.
Okay. Hmm.
But how signal also should be cancelled, no? But signal
Yeah.
will not be cancelled because left side the gain is minus GMRC by 2. Right side it is going to be plus GMRC
Plus
by 2.
GMRC by 2.
So only signal will be amplified. The common problem, whatever the common changes are there due to temperature, VBC simple. Your VB, can you see my hand? Okay, I've switched off the video, right? Okay. Now can you see?
Yes, sir.
Yeah. So whenever temperature is there, the voltages will rise like this. Like this. By same amount. When you apply signal, it will go like this. One is plus and the other one is minus. But temperature is a common problem. It will create same perturbations. So differential amplifier is so clever that when you take the difference, what will happen when this side goes up by 1 millivolt, this side also goes up by 1 millivolt. Those common changes when you subtract, they will get cancelled, no? Are you getting?
Mm-hmm. Yes, sir.
Any common voltage changes, right? AC means not voltage, the change in voltage. When the change in voltage is like this, it will get cancelled. When the change in voltage is like this, one up, one down, then the middle point will be at virtual ground. One is minus 10 gain, the other one is plus 10 gain. When you take difference, it will be minus 20. The gain is going to be minus 20. The gain will be
So
double. Are you getting?
virtual ground when it is connected to a current source, right?
With respect to emitter, these two are going to dance like this. That is called the differential dance. That is why this amplifier is called the differential amplifier. One end goes up, the other end comes down. Are you getting? Like a
Yes,
kid,
sir.
like a kid who plays seesaw in a park, right? There are seesaws where one kid will go up, the other kid will come down, but the
Yes,
middle point will never move.
Yes, sir.
So you can place a book in the middle that is exactly at the zero node. It is not going up by 1 volt or coming down by 1 volt. The book will not fall if you put in the middle, but this guy will go up, this guy will come down. Have you seen?
Yes, sir.
So
Yes,
that
sir.
middle book where you are putting, that's the emitter node. It is at zero.
Okay. And so 39F.
Yeah. Yeah.
So here, how is this method working?
Yeah, simple. Left side, you are getting minus x by 2.
Hmm.
Right side, you are getting plus x by 2.
Yes, sir.
But if you take difference, you are getting x. Now the question is, who is this x? X is Adha circuit. If you take half circuit, you are getting V0 by V as minus GMRC, no?
So I have how is this 1/2 factor not coming into picture here when we are calculating for just one half the
No, because 1/2 plus 1/2 is 1, no? Minus 1/2 minus of minus 1/2 is 1.
But when we are calculating for half of the circuit, it should also be there now. When
But half of the circuit we have given full signal, no? Other
Okay.
circuit, pura signal. Pura
Okay.
circuit, other signal you have given.
Okay.
Are you getting? See,
Yeah, I got it.
only one cake is one. So that cake should go to the stomach. But 2 people are eating or 1 people are eating, it depends, no?
Okay.
One fellow is eating full cake, half circuit full.
Mm,
Here
so
2 people
one
are
time-
eating, but half they are eating.
Okay, sir. So in 42F, there's one silly doubt. We take virtual ground when that point is connected to a current source, right?
No. We'll
Then-
in the line of symmetry, in the middle we have to take. One end goes up, the other end comes down, I told you, no? See, this point goes up. See, what you mean by differential amplifier is, please observe here. Anything that you find at left side of the amplifier, if you see the right side of the amplifier, it will be exactly 180 degrees phase shift.
Yes, sir.
Are you getting? So
Yes, sir.
basic differential amplifier you take, you sketch VC1, VC2, if somebody has given you VC1 positive waveform, here negative will be there. If this is negative, that is why it is called differential. Complete opposite. Here all the voltages, if they rise up, or all the voltages at the right side will come down. So if that is there, if this end, can you see my pen here?
Yes, sir.
If this end goes up, this end comes down, middle there should be 0, no? So I'm
That's
splitting.
when we take the virtual ground.
So
Okay.
because if I locate the virtual ground, I know that Adha circuit gain and Pura circuit gain are same, no?
Okay.
So this is a network analysis technique I'm using. I'm locating a point P, I'm cutting it into 2 parts. Adha I got. So gain of Adha is gain of Pura.
Thank you so much, sir. I got it. Thank you.
Yeah.
Hello, sir. 33F.
Hello.
What?
33F.
Yeah. Tell me.
Sir, here we have same signs now, sir. I mean base emitter plus Vn by 2, and there will be B2 and E also plus Vn by 2 will be there, no, sir.
Yes.
In
No.
circuit and
This is dynamics. No, current is there in a loop. See here, this is the current direction. Can you see the current?
yes, sir.
Current means plus minus, you have to write. With respect to what you are measuring voltage, that is different. Polarity is how you can change. Current will go till emitter and then come back. It will not come back, no. It will flow in a loop. When it flows in a loop, how you will take? Are you getting? Voltage is different. Current, how you can change? See here, I am having 10 resistors like this. And I have given a common voltage. How current will flow? Like this only, no?
But their forward bias we have to take like
No,
basic.
please, 0.7 is only for DC analysis. Resistor is for AC analysis. That is the rule you have to understand first. 0.7 volt is not there in AC analysis. R pi is there. That is a dynamic resistance. Resistance does not have polarity.
Okay, sir.
Resistance does not have polarity. Okay.
Yes, sir. 31F, sir.
Huh?
31. 31.
Yeah.
Sir, here you said that, so then Rn will be 0 na, sir, short circuit mein.
Rn, current 0 means infinite resistance.
Voltage short mean resistance will be
Here current Ig is 0, no? For In is 0. What is resistance? R equal to V by I. Your In is 0. Denominator 0 means it is infinite, no?
Sir, but voltage short mean resistance will be 0. Na, sir.
Where voltage is short?
Here you given second diagram, second circuit.
That is to calculate. This is calculation of output resistance.
Okay.
Calculation of output resistance, not input.
Okay.
Of
35, sir.
yeah.
Sir, here we have symmetry in the circuit. So we have taken I0 by 2 and I0 by 2, right? Sir?
Yes.
Okay.
This is DC.
And
No? This DC part we have done in the beginning of BJT course. The current I0 is going to split it into two parts. DC means you have to take diode, not resistor. This is 0.7. This is also 0.7. So now the current will split it into two parts. This DC analysis.
and 14,
Your voice is not clear.
14F. Hello, sir. I'm audible.
Your voice is not clear.
14F, sir.
14F. Yeah.
Sir, here why you short circuited gate and drain, sir?
This terminal is called gate. This terminal is called drain. There is a short here. That is why we have shorted here to calculate.
Okay. One more doubt, sir. 6F.
Huh?
6F. Okay, sir. No doubt, sir.
Okay.
Thank
Next.
you.
Sir, 14F. Sir, in this rule 4, I'm not getting, sir. How this R naught is equals to R naught plus 1.
I have proved, no? You have not attended yesterday's class?
No, sir, I attended.
I have proved for, I've taken the small signal model for it. Wait, let me see if I have yesterday's. Yeah. Can you see here?
Yeah.
Can you see?
Sir.
So I have a MOSFET with a resistor R here. Can you see? I want to calculate the resistance here. So I connect one voltage source. I've given current. So then I applied KVL. First one KVL here and another KVL here. I got this 1 plus GM R0.
Okay.
It is 34 page. Can you check the KVL? Okay.
Okay, sir.
Yeah.
Okay, sir. Thank you.
Yeah. Yes.
Hello, sir.
Yes.
Sir, my doubt is in MOSFET current equation.
What current equation? Hello.
Hello, sir.
Yeah, tell me.
Sir, my doubt is in MOSFET current equation, sir.
Yeah, tell me.
Sir, actually, while studying in college, I studied that for NMOS and PMOS, the current equations are different, sir. Like for NMOS, it is mu n Cox, and for PMOS, it is mu p Cox.
Yeah. Mu n, see, mobility is same, generally examiner gives. Otherwise, in none of the problem we have change in mobility, no?
Sir, that's why I got
Mu
confused,
Cox
sir.
W by L is mu n Cox W by L or mu p Cox W by L. Yes.
Sir, mu n and mu p are same, sir.
Yes. Because complete gate problems runs on W by L ratios. In fact, designer also has only that in hand to change width and length.
Okay, sir. Means I was confused, sir, because
No, you are
while doing problems, we
no,
cancel
you are
both
100%
mu's.
right. The reason being, if the examiner says that W by L1 equal to W by L2, all other parameters are same, he will say.
Oh, okay,
He
sir.
says all other parameters are same, then the Cox is same, then mu is same.
So we can cancel directly, sir.
Yes. Now you got it.
Oh, okay, sir. Means we have to concentrate mainly on W by L ratio.
That is a designer's perspective. No? With that only you will design. See,
Okay,
when you
sir.
send a MOSFET for fab, with that W by L ratio, they will create. Mobility we don't have, no? It is
Yes,
not
sir.
in our hands.
Only the length of channel is in our hand.
Yes, you're right.
Okay, sir. That was my doubt. I was waiting for 2 days.
No, you're right.
Okay, sir. Thank you, sir.
Okay.
Okay, sir. Hello, sir.
Next.
Hello, sir.
Hello, sir.
Yes.
Sir, today's starting 2F, 3F, sir. Page number 3F.
Yeah.
Previous one, 2F. Hello, sir.
Yeah.
Sir, in this, how did you got R0, R02? R02.
In third problem or fourth problem?
Third problem.
Third problem, yeah. See, this terminal is drain terminal. This terminal is what? Drain. Okay.
Drain.
So when you suppose this terminal is the base terminal, then you will have to write R pi. If this terminal is emitter terminal, then you have to write 1 by Gm or alpha by Gm. But this terminal is drain. So when somebody sees from here, what does he see? He's seeing R0. Are you getting?
Yes, sir.
Yeah. But in another problem, what I did is, can you see here, if somebody sees from here, what is the name of the terminal? This terminal. This is called the base terminal. That is why there is R pi.
Okay.
Are you getting?
Yes, sir.
Yeah.
With respect to drain, it is R0.
Yes. With respect to base, it is
gate.
With respect to emitter, it is alpha by Gm.
With respect to base, R pi.
Yeah.
Sir, in emitter, negative resistance, sir. negative output.
In common emitter, negative output.
Sir, in this ninth problem, 6F page number.
This one, huh?
6F, sir, 6F.
Okay.
Sir, RC equal to infinite also.
Current source, just now I told, no? Current source means it is a amplifier with high output resistance. That is why all current sources should be replaced with open circuit in Thevenins.
Okay.
All voltage sources should be replaced with short circuit in Thevenins. Current source means open circuit. When you draw AC equivalent, what you'll do? When you draw AC equivalent, current sources should be removed. Yes or no?
Yes, sir.
And who is there in the place of current source? RC is there. So I'm just putting RC infinite. Just for time pass I have done. Otherwise, there is no RC. Only transistor is there. It will give you minus GMR0, no?
RC parallel to R0 also.
Can you see?
Yes, sir.
In this small signal model, R0 is there. That's all minus GMR0 you will get. There is no question of RC in the circuit because RC has to be replaced with, the current source has to be replaced with open circuit.
If RC is there, RC parallel to R0 also.
If RC is there, then RC parallel R0. If RC is not there, then infinite parallel with R0 is R0.
Okay.
Hello, sir.
Okay, next.
Hello, sir.
Anybody else?
Hello, sir. Hello, sir.
Anybody else?
Sir, hello sir, good evening sir.
Yes.
Sir, what does the statement capacitor blocks DC exactly mean, sir?
It means that it will charge, that's all. When will you say that you will block the food? Suppose your mother wants to feed, right? You say you block, I don't want. When you say you don't want, that means already till stomach full you have ate.
Yes, sir. Yes, sir.
That is why you are saying we don't want. So capacitor blocks DC means it is fully charged.
Okay.
And that whole voltage is across that capacitor.
Okay. Sir, and one more doubt, sir. Sir, charging speed depends upon the adapter or cable, sir?
Which one?
Practically, sir, mobile phone charging.
Tau only, tau, always tau. And the cable can be a factor also. But through what elements you want it to charge? We have to see, no?
Okay, sir.
Because cable means what? Resistance is negligible.
Okay.
But the charging elements inside we have to check. How, with what path it is charging.
Okay.
That path if you track, then we will know. Tau.
Okay, sir.
Okay?
Okay. Thank you, sir.
Yeah. Next.
Hello, sir. Hello, sir.
Yes.
Hello, sir.
Yes.
Good evening, sir.
Yeah, good evening.
Sir, in 5F and 6F, if we compare the problems, both are getting same answer, sir. Just RC is infinite in the ninth problem, right, sir?
Yeah.
Here RC is parallel to R0.
Yeah. RC is not there, first of all, because its current source is there. So I just want to compare it with the common source or common emitter amplifier.
Okay.
So because current source is there, so I said, okay, if there would have been an RC here, it would have been infinite. So you substitute infinite and say. Otherwise, underneath small signal model is there, no? Only R0 is there. Minus GM R0 you will get.
Yes, sir.
Yes or no?
Yes, sir.
Yeah.
Sir, 9F.
Yeah.
Sir, here we are taking R0, sir.
Where?
So this problem I didn't get, like are not parallel we are taking, right, sir?
Yes. See, there are three things here. One is resistance seen through emitter,
Yes, sir.
which is alpha by Gm plus Rs from this point 1. And from 1 to ground, there is Re. From 1 to ground, there is R0. Three are there, no?
Okay, we are seeing through emitter.
Yeah, because output resistance is here, no? R0.
Okay, sir. And if with see through collector, then that general formula is there, that we need to write, sir?
Yeah, R0 plus 1 plus Gm R0.
Yes,
You're right. Absolutely right.
Yes, sir. That I was getting. And sir, 11 and 12F, sir. Sir, actually, that I lost my connection, sir. 11 and 12F.
This is just a definition, that's all. Definition, we have introduced small signal model for MOSFET, no?
Yes, sir.
So the GM we are introducing. How do we get GM? We have to differentiate. When you differentiate, we got that value mu Cox W by L VGS minus VT. So this AC analysis, whatever we are doing, you have to get from DC. From DC, you have to get this value VGS minus VT.
Okay.
Yeah, and similarly AC analysis, ID VDS curve R0 is there. Only these two are there in the MOSFET. Can you see? Here there is GM, here there is R0. Can you see here?
Yes, sir.
Only these two, no?
GM and R0.
So
Yes.
GM definition, R0 definition, that's all I've given.
Okay, sir.
Okay.
Sir, one more doubt, sir. Sir, 18F, sir. Sir, like what is difference between parallel connection MOSFET and the diagram which you have written, third diagram? Both are same, sir?
Both same. This is to save ink, that's all.
No, sir, you have shorted two MOSFETs.
No, I didn't short. I just draw a straight line. But fact is, this from this point to this point, there is a connection.
Okay.
So it has to go. No, nobody will draw like that, no?
This one and parallel connection both are same, right, sir?
This is parallel only, no? Parallel means what? Parallel means what, you tell me? Parallel means two resistors in parallel. What do you mean by that? This is 1, this is 2. This is 1, this is 2. Both should be shorted.
Okay, sir.
In a BJT, there are 3 terminals. So these two should be shorted. These two should be shorted.
Got it.
And these two should be shorted.
Okay, sir.
But we cannot draw like this, no? So they will draw one line in the middle.
Okay. Sir, 36. Sir, this I didn't understand, sir.
Yeah. See, for VIN to cover a loop, there are 2 VBs, no?
Like KVL, we are taking both the KVL. Like first, we are taking above KVL and below
Above
KVL.
KVL is for V0. Below KVL is for VIN.
Okay.
See, the point is, when can you write the ratio of voltages equal to the ratio of resistors? The ratio of voltages is ratio of resistors only when numerator current and denominator current are same, no?
Yes.
So I have to imagine IC flowing in this upper loop. I have to imagine IC flowing in the lower loop. If I imagine IC flowing in the lower loop, what is VB? VB is equal to IC into 1 by GM, no? Or GM is IC by VB.
Sir, when we are considering lower loop, we are considering only VB1, sir.
VB1, VB2 together is VIN.
Okay.
Because VIN plus terminal is here, minus terminal is here. It has to cover a loop. Can you see what is a loop? Loop means you start at one point, this is start point. And you have to come back to the same negative terminal like this from here. Like this.
Yes, sir.
That is called a loop. So it covers both the VB. That is why 1 by GM plus 1 by GM.
Like actually we are taking in the answer left side and right side, right, sir?
Left side is current is coming from the ground, so negative. If current goes to ground, it is positive.
In left side, current is
coming from the ground. So I is 0 minus VC by R. Say you can take I, Ohm's law you have to apply. Ohm's law says that I equal to V1 minus V2 by R. So it is 0 minus VC1 by R.
By R. Okay. In the right side, it is going towards ground.
So I equal to VC minus 0 by R.
0 by R.
That is basic Ohm's law. I equal to V1 minus V2 by R.
Okay, sir.
Yeah.
Sir, but method 5 is very easy, sir.
Thank you.
Sir, and last.
Any method you can follow. Even the last method I told, no?
Yes, sir.
Gain of full equal to gain of half. That is also you can apply. This way you can, these are all techniques to avoid small signal.
Yes.
Otherwise, small signal means one differential amplifier with resistors will take 45 minutes it will take. Kirchhoff's law you have to apply and headache, no?
Yes, sir. Actually, I have not noted down the short signal terms only, sir. These methods are very simple.
Okay.
Sir, and the last problem, sir.
Yeah. This one.
Yes, sir. This one is, this one can you explain, sir?
This is a common source amplifier. This is acting like a load. This load.
Okay, sir. But here also parallel connection, right, sir?
Huh?
Parallel connection above.
Yeah, this is separate you can write. This is V bias, this is V bias you can write.
Okay, sir.
Separate.
Okay, sir. Got it, sir.
Yeah.
So today's class is very interesting, sir.
Thank you so much.
Thank you, sir.
Yeah.
Hello, sir.
Yes.
Sir, in today's starting problem, sir.
Yeah, tell me.
We taking R01 with respect to collector, no, sir. That is a rule or finding R0 we conclude the.
Which one is a rule?
While finding the R0, consider virtual effect.
Yeah, if one end goes up, other end comes down, that point will not have any dynamics, no?
We while considering the R0 one.
In which paper, yeah?
Sir, 3F over page number 3F.
Yeah.
We draw with the R0 one, no, sir.
Yeah.
Register.
Yes.
This only for finding the R0, no, sir.
Output resistance, yes.
For a common source and common emitter, output is minus, no, sir.
For common source and common emitter, output is negative, yes.
Sir, once open the common source amplifier problem, sir. Page number 15F.
Yeah.
In this second question, how you calculate the V out by Vx, sir?
V out by Vx, sir?
Yes.
For that, you have to draw this separately, like this. This is first one only, no?
Yes, sir.
First one answer, you can substitute here.
RD parallel to R0. While we consider minus GM, sir. GM. There is no resistor, no, sir.
Where there is no resistor, V0 by Vx is minus RD by 1 by GM, no?
1 by GM.
That is minus GMRD only.
Okay. Hello? Sir, 17F.
Yes. Yes.
Hello. Am I audible, sir?
Yeah.
Sir, page number 41F.
Yeah.
Sir, here you did that Bean distributed into Bean minus that part I did not understand, sir.
Acha, down one.
Yeah.
You can write, so in some questions, they will simply put V in between the two gate terminals.
Okay.
In some questions, they were writing V in 1 and V in 2. Both are same, I'm saying. V in is the potential difference between the two base terminals. V in 1 is the voltage from here to ground, from here to ground. If you apply KVL, V in between the two is nothing but V in 1 minus V in 2.
That's it, sir. Thank you.
Are you getting?
Yes, sir. Yes, sir. Got
Yeah,
it.
you can put V in here. Otherwise, from here to here, V in.
So in a question they can give like one V in or V in.
If they give one V in, or if they
Then you
give
have
V in
to-
1, V in 2, it's one and the same.
Okay, sir. Got it, sir.
Okay.
Thank you, sir.
30th. How R naught is very high? RD parallel R naught plus something should be RD, right?
Yeah, this portion is high, I'm saying. This portion is high, that is why it is approximated to RD.
So is it RD is high or what?
No. This portion is high. This portion of R naught is high.
Okay.
High
Then,
value, I will write this portion is high value. That is why it is RD.
okay. Then common gate amplifier need not have a high R naught. Well,
No, if your output resistance is suppose your RD is the load, then what will be your output resistance? Down. You have to see down, no? Like this.
okay.
Because RD is load, then you will have tremendous output resistance.
Okay, sir.
Are you getting?
Yes, sir.
Yeah.
Sir, and in rule 3 of resistance reflection, Rin is R pi plus 1 plus beta times Ra, right?
Yes. Right.
I is in the I2 1 plus beta times I. So R has to be decreased, right? Because current increases.
Where you are saying? In the BJT, yeah?
Yes, sir.
In BJT, your V in equal to IB into R pi plus IE into RE. But IE is 1 plus beta times of IB. In that loop, you have to imagine a single current flowing.
Okay.
But if there is any multiplication factor for the current, that you have to associate to that resistor, no?
Okay. It is not like that current increases, resistor decreases.
That is at the input side. See, I am asking you to find the resistance at input. Will you think about that current or will you think about somewhere current in other branch? If the input current is IB, base current is small, resistance will be large.
Yes, sir. Okay.
Are you getting?
Yes, sir.
By what factor it is large, you have to go inside and check. If there is an emitter current, you have to multiply that resistor by 1 plus beta. That's how the base current at the input is giving you a larger resistance overall.
Okay, sir. Yes, sir. Got it.
Yeah.
Sir, I have a doubt in differential amplifier, sir.
Yeah. Page?
General one, sir. Sir, you said one transistor will give high cycle and other transistor will give low cycle.
Very good.
So,
If the one is positive cycle, the other one will be negative.
So if we see then, if both coincide, if we check the output, then the output should be a DC signal, right, sir?
It should be doubled, no? Because what you said is correct. If you add it,
yes, sir.
This is not an adder. It is a difference amplifier. Difference means that voltages you have to take minus again. If one end is minus 1, the other end is plus 1. If you take minus, it will be minus 2.
Oh, okay, sir.
Are you getting?
Yes, sir.
Already they have 180 degree phase shift, but at the same time, in the middle you have to take difference. Then it will get amplified 2 times. Minus x by 2 plus x by 2. If you take difference, it is x, no?
Yes, sir. Sir, what happens to current, sir?
What currents?
The input current, does it amplify change or does it reduce in the output side? for differential
See,
amplifier?
the differential amplifier input resistance is high. You're giving it suppose to the gate. It's only the signal, no? You'll apply a signal and change the dynamic of IC.
Yes, sir.
So the current that is coming from the supply is changing based on the VB voltage. If your VB is plus, your IC is going to be GM times of that. If your VB is minus, accordingly negative.
Okay, sir. Sir, I have one general doubt, sir. Sir, all the methods you have explained, I understood them, sir. Just
Very
can
good.
you just, but I'm unable to connect all of them.
No,
Like
no, no.
it's
There's no
it's a
need.
bit
The point
it's a bit
is all roads meet at Rome, no? It is not. See, first of all, I'm giving you 4 different methods. Again, they are called different methods. Why you don't want to find a similarity in those different methods?
I have a confusion between which method to use between BJT and MOSFET. Like
No, BJT MOSFET, we have used only that 4th method, no, to solve if there is symmetry.
yes, sir.
Or
And
you can use second method directly 1 by GM, 1 by GM. You add. What is it?
okay. And
Second and fourth you use. Rest else you discard.
yes, sir. Okay, sir. That was.
Okay, right.
Sir, if possible, can you summarize the everything, sir, tomorrow, at least in tomorrow's class?
Okay.
Yeah, thank you, sir.
Yeah.
Hello, sir.
Yes.
Page number 21, sir. In this, V bias equal to how 0, sir, for AC analysis, sir?
No, that you have to put VDD into R2 by R1 plus R2. That is a DC voltage. That voltage is connected to ground for AC analysis.
Okay, sir. Means VDD R1 R2 will negative.
See, for AC, let me tell you, for AC, this is ground, no?
Yes, sir.
When this is ground, that voltage is 0 only, no? For AC.
Yes, sir.
Yeah.
Sir, in 27, 26, sir.
Yeah.
Sir, in this second problem, how you got a GM output, GM1 R0?
R0, this is R01 is mega ohm plus mega ohm plus mega ohm into mega ohm.
You neglect R01 and R02.
R01 into R02 is very big, no?
Yes.
That is why. It is like 1,000 rupees plus 1,000 rupees plus 1,000 into 1,000.
Okay, sir.
Yeah.
Sir, in this VN not calculated.
VIN should be grounded for AC and for output resistance. Your VIN should be shorted.
Okay. Thanks.
Yeah.
Hello, sir.
Yes.
Sir, in the differential amplifier, how to eliminate capacitor? You said 3 points, no, sir.
Yeah.
In that, output capacitor is not needed as the VDC is cancelled by differential measurement.
Yeah, output capacitor. Some DC will be there. In common emitter, some DC will be there, no? So the DC is blocked by that capacitor. In differential amplifier, suppose left side you have 6 volts, right side also you will have a DC of 6 volts, no? Then when you take difference, 6 minus 6 is 0. DC, only AC is going to have differential. DC same voltage, no? What is DC voltage? See DC analysis of differential amplifier. Did I give you DC analysis of differential amplifier?
Yes, sir.
In that I naught is split into 2 parts, no? I naught by 2. Suppose I naught
By
is
2, I naught by 2.
here. 0.5, 0.5 will be there. And what is voltage at collector VC1? It is VCC minus I naught by 2 into RC. Right
Yes,
side also
sir.
same. So when you take difference, when common noise is getting cancelled, why not common DC I'm saying?
Okay, sir.
Are you getting?
Yes, sir.
Yeah.
Sir, and you said about the passive load and the active load, no, sir?
If a resistor is connected, then it is passive load. If a transistor is connected, in the place
Yes.
of resistor, it's called active load. Because
Sir,
transistors
in
are
one,
active elements.
sir, in one transistor, if they are in series, for one resistor, there if one resistor is there, for other, directly we connected the VCC. In that condition, how will we calculate, sir?
What?
So in this method, see, we have one diagram, it's a differential amplifier. For one MOSFET, we have RD resistor. For another, we don't have the resistor. Directly, we gave one transistor to the VCC and another with the resistor we are giving. In that case, we have to consider that as active load or passive load, sir.
Which one? 1 by GM or RD?
No, sir.
Which one?
Just for one transistor, you said about the passive load and active load, no, sir.
See, suppose this transistor is there. Upper one, this is called active load. Active load.
Yes, sir. For that load, if we take from VCC, we take one resistor, and for that
it is passive load. If you connect a resistor, physical resistor from VCC, it is passive load. If you connect a transistor, it is active load.
If both connected means then?
Both connected means one is mega ohm, the other one is in kilo ohm. 1 mega ohm plus 1 kilo ohm, still active only, no?
Okay, sir. Sir, what is composite transistor, sir?
Composite means combining them. Combining a parallel connection can be a composite. Darlington pair can be a composite transistor.
Okay, sir. Sir, one small doubt. In amplifier, if you want to reduce the bandwidth, means there is a 1 bit on that. Which compensation should we use, sir?
To reduce bandwidth?
Yes, sir.
Frequency compensation only. Frequency compensation.
Sir, in that option is not there, sir, I think so. Pole zero.
Yeah, that frequency compensation is the pole zero compensation. Dominant pole compensation.
Yeah, yes, sir, that one.
Yeah.
Okay, sir. Sir, in the most of the previous gate papers, they gave the HIE, HFE, H parameters.
That is 20 years back, when our parents were writing gate, no?
No, sir, in 2005, 2006, 2008 also.
No, I don't. No. In one problem, HIE infinite. So HIE is RPi. HIE is RPi. Tomorrow I will give you what we are using is H parameter only, no? But I am not naming it as H. It's like suppose in your house you have two names, but your friend does not know that you have a second name, a pet name, which your parents only know, but you are the same person, no? So similarly, this BJT MOSFET, what we are using is H model only, but I am not mentioning it as H. So tomorrow I will equate them. Okay. RPi is HIE. Like that, R0 is 1 by HOE, I will tell tomorrow.
Yes, sir. As we are completed the BJT and MOSFET, I was searching the previous papers, and in that they mentioned that is BJT and MOSFET, but in that they gave HIE, HFE, but I was really confused.
This is RPi only. It is no different.
Okay, sir.
Okay.
As we are doing the problems, it is very easy and we can do any problem. But when I see the previous questions, I was a little bit
you need
confused.
practice, yes.
Yes. So please tomorrow compare both. Sir.
Sure, I'll compare and give.
Okay, sir. Thank you so much.
Right.
Hello, sir.
Yes.
Sir, differential amplifier, fifth method once open.
Fifth method.
Yes, sir.
Gain of full circuit is gain of half.
Yes, sir.
What is there? Just a half circuit you have to draw. That's all.
Sir, in that V out equal to VC1 minus VC2, V in equal V1 minus V2. Oh, sir.
No, if you are getting minus GMRC, no?
Okay, sir.
The gain is minus GMRC. Left side, if you take minus GMRC by 2, right side, if you take plus GMRC by 2, you will get, no?
Okay, sir. Sir, last second problem once over. Last 2 seconds.
Page. This one, huh?
Next one. Sir. How you draw the AC equivalent circuit, sir?
Okay. Voltage sources should be short. Current sources should be open.
Okay, sir. Sir, 2 resistors, however, VDD by VDD, you take VDD by 2, VDD by 2.
And that middle point will be at virtual ground.
Okay, sir.
That is how you have symmetry. You can cut it into 2 parts.
And you take an off the part and calculate.
Because gain of half is gain of full.
Okay, sir. Thank you, sir.
Yeah. Okay, shall we stop? Anybody else?
Hello, sir.
Yes.
Sir, can you explain the loading effect once again, sir?
Which loading?
Sir, you told your incidence, sir, in company.
That was, see, it's very simple. What is there? Before connecting the load, whatever signal is there, after connecting the load, same signal should be there. Then there is no loading. Before connecting the load, you have some signal, but after connecting the load, same signal is not there. Means there is some voltage division like this. This is 9K, 1K we took, no?
Sir.
Suppose this is 10 sin T. Before connecting the load, it was 10 sin T. After connecting, it became 1 sin T. Then this is loading. It should be 10 sin T here, 10 sin T. But even after connecting load, if you want same 10 sin T, then you have to connect it to an amplifier here, whose input resistance is, this is 10 sin T, this is 9K. Here you have to connect 1K.
Input buffer.
So input resistance, current will not be there, 0. So you will have 10 sin T. Same 10 sin T will appear here.
Okay, sir. Thank you, sir.
Yeah. Okay, shall we stop?